1 light year sounds like a distance problem. Build a fast enough engine, point it at the stars and go. 5.88 trillion miles, a number so large it loses meaning the moment you say it out loud. But here is what almost no one tells you. The distance is not the hard part. The distance is not even close to the hard part. At 99% the speed of light, your 1-year journey ages Earth by 7 years. Your bones lose 1 to 2% of their density every month you spend in microgravity, dissolving into calcium dust your body can no longer hold. The so-called empty space between stars becomes a particle storm, moving so fast that a single hydrogen atom hits your hull with the energy of a hand grenade. Cosmic radiation delivers the equivalent of more than 150 chest X-rays every single day, with no atmosphere, no magnetosphere, no planet to hide behind. And your mind, isolated at a distance no human psychology has ever been tested against, begins to fray in ways we have no data to predict and no protocol to prevent. This is not science fiction. This is physics. Cold, indifferent, and utterly unforgiving. The universe does not care how advanced your technology becomes. It does not care how badly you want to reach another star. It only asks one question: how much are you willing to lose? We have spent decades romanticizing interstellar travel as humanity's next great leap. But we have spent almost no time being honest about what crossing 1 light year actually does to a human body, a human mind, and the fragile ship that carries both. This video is that honesty. And by the end you will understand why the stars are not waiting for us to arrive. They are waiting to see if we survive the attempt. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. 1 light year is 5.88 trillion miles. Say that number out loud. 5.88 trillion. Your brain will attempt to picture it. It will fail. Not because you lack imagination, but because human cognition did not evolve to process distances where the number of zeros starts to look like a formatting error. A trillion of anything sits outside the boundary of what our minds can truly hold. We can say it. We can write it down. We cannot feel it. Not really. And that gap between what we can measure and what we can comprehend is where the entire fantasy of interstellar travel lives. For most of human history, distance was something you could walk. A day's journey, a week's ride, a season at sea. The farthest anyone could go was still a place you could in theory reach by putting one foot in front of the other and refusing to stop. Then we built machines, cars, trains, planes, distance compressed. What took months became hours. What seemed unreachable became routine. By the mid-20th century, we had rockets. We pointed them at the moon and we got there. 8 days round trip. We looked at Mars and thought, sure, a few months. We looked at the outer planets and thought, okay, a few years. The pattern held. Build a faster machine, shrink the distance, go farther. The logic was clean. Everywhere in the solar system could eventually be reached if you were willing to wait and if your engine was good enough. Then someone did the math on the stars. The nearest star to our Sun, Proxima Centauri, sits about 4.24 light-years away. That translates to roughly 25 trillion miles. Using current propulsion technology, the kind that got us to the outer planets, a trip to Proxima Centauri would take somewhere in the neighborhood of 70,000 years. 70,000. That is longer than recorded human history, longer than agriculture, longer than the oldest known cities. You could launch a spacecraft today, and by the time it arrived, the civilization that built it would be unrecognizable, assuming it still existed at all. And that is just to the closest star. Most stars are farther, a lot farther. The galaxy is roughly 100,000 light-years across. To travel from one side to the other at the speed we currently move through space would take billions of years. The universe itself is only about 14 billion years old. You would age the cosmos. So the obvious answer, the one that shows up in every conversation about interstellar travel, is to go faster, build a better engine, apply more energy, accelerate harder. If 70,000 years is too long, then do not take 70,000 years. Go at 1% the speed of light and cut the trip to Proxima down to a few centuries. Go at 10% and you are looking at decades. Go at 50% and suddenly the nearest star is within a human lifetime. Problem solved. Break out the champagne. Except that is not how physics works, and the faster you try to go, the more violently the universe reminds you of that fact. Let's start with what 1 light-year actually is. Light, the fastest thing in existence, travels at roughly 186,000 miles per second. It crosses the distance from the Earth to the Moon in about 1¼ seconds. It reaches Mars in under 13 minutes when the planets are close. In 1 year, light covers just under 6 trillion miles. That distance, from January 1st to December 31st at maximum speed, with no obstacles and no stops, is what astronomers call 1 light-year. It is not a measure of time, it is a measure of distance. A ruler built from the only thing in the universe that does not slow down. The confusion is understandable. The word year sits right there in the name, and our brains want to treat it as a duration. It is not. A light year is exactly as much a unit of time as a mile is. You would not say a mile is 20 minutes. You would say a mile takes 20 minutes to walk. The mile itself is still just a length. Same with a light year. It is a length, a monstrously, incomprehensibly large one. To give you a sense of the scale, imagine you are standing at one end of a football field. The opposite goal line is 100 yards away. You can see it. You can walk to it in under 2 minutes. Now imagine that football field represents the distance from the Earth to the Moon, roughly 240,000 miles. You are standing on Earth. The Moon is at the far end zone. The Sun, in this analogy, would be sitting about 400 football fields away. Proxima Centauri, the nearest star, would be roughly 100 million football fields away. If you tried to walk that distance at 3 miles per hour, you would be walking for about 900 million years, and that is just to the nearest star. Most of the stars you see in the night sky are hundreds or thousands of light years away. Some are tens of thousands. The Andromeda Galaxy, the closest large galaxy to our own, is about 5 million light years distant. Stand outside tonight, look up, and find Andromeda if the sky is dark enough. The light hitting your eyes left that galaxy before modern humans existed. You are not looking at Andromeda as it is. You are looking at Andromeda as it was when our ancestors were still figuring out how to sharpen rocks. That is what a light year does. It pulls the past into the present. It turns the sky into a time machine where everything you see is gone, changed or dead, and you are staring at the corpse of a moment that will never return. And if you want to travel that distance, you are not just fighting space, you are fighting time itself. Humanity has been dreaming about interstellar travel for as long as we have known the stars were other suns. The idea shows up in fiction as early as the 17th century, in Johannes Kepler's Somnium, a story about a journey to the moon that doubles as a thought experiment about what it would take to leave Earth entirely. By the 20th century, the dream had fully metastasized into popular culture. Science fiction gave us warp drives, hyperspace, jump gates, generation ships. Every storytelling tradition invented its own shortcut because the actual distance was too large to narratively tolerate. Writers understood what audiences did not. If you showed the real math, the story stopped. No drama survives 70,000 years in transit. No character arc holds across a millennium. So we invented magical engines and moved on. The public absorbed the aesthetics without absorbing the physics. We saw ships jumping between star systems in minutes. We watched crews arrive at distant planets within the runtime of a 2-hour movie. And somewhere in the back of the cultural mind, the assumption settled in that interstellar travel was a matter of when, not if. That it was an engineering problem, not a fundamental limit. But once we got serious, once we built the right machine or discovered the right fuel, the stars would open up the same way the moon did in 1969. All we needed was funding, focus, and a faster engine. That assumption is wrong, not optimistic, not premature, wrong. Because the problem is not the engine, the problem is the distance, and the distance does not care how clever you are. Imagine you are holding a marble. That marble represents Earth. Now place a second marble 4 miles away. That second marble is Proxima Centauri to scale. You are standing next to Earth and you want to get to Proxima. You have a bicycle. At 10 miles per hour, the trip takes about 24 minutes. Not bad. Now someone tells you the marbles are not 4 miles apart. They are actually 25 trillion miles apart. The bicycle does not help anymore. It does not matter if you upgrade to a car. It does not matter if you upgrade to a jet. You can ride a rocket and you are still looking at tens of thousands of years. The issue is not your vehicle. The issue is that the gap between the marbles is so large that human scale speed has become irrelevant. You are not stuck because you are slow. You are stuck because the universe is big in a way that does not compress no matter how fast you go. And here is the part that really stings. Even if you could go fast, truly fast, a significant fraction of light speed, the journey itself would kill you. Not eventually. Not after decades of slow decay. Immediately, violently. In ways that most people never think about, because most people assume empty space is actually empty. It is not. Space, the stuff between the stars, is not a vacuum in the way a laboratory vacuum chamber is a vacuum. It is not perfectly sterile. It is not inert. It is full of things. Hydrogen atoms, mostly. Roughly 1 per cubic centimeter on average, which does not sound like much until you realize that traveling at even a modest fraction of light speed means you are slamming into billions of them every second. At low speeds, they bounce off harmlessly. At 10% the speed of light, they hit like bullets. At 50%, they hit like bombs. By the time you approach the speed of light itself, every hydrogen atom you encounter carries the kinetic energy of a small nuclear weapon. Your ship does not get dinged, it gets vaporized. The interstellar medium, that faint haze of gas drifting between the stars, becomes a particle accelerator pointed directly at your hull, and there is no shielding thick enough to stop it. Then there is the radiation. Space is soaked in it. Cosmic rays, high-energy particles flung out by supernovae, pulsars, black holes, and the sun. On Earth, we are protected by a magnetic field and an atmosphere that absorbs most of the incoming radiation before it reaches the surface. In space, you have nothing. A trip to the moon exposes astronauts to about as much radiation as a chest X-ray. A trip to Mars, which takes roughly 6 months, exposes them to the equivalent of a full-body CT scan every week. A trip lasting years or decades, crossing the void between stars, exposes the human body to cumulative doses high enough to shred DNA, trigger cancers in multiple organs, and destroy the bone marrow that produces blood cells. Your immune system collapses, your brain begins to swell, your vision deteriorates, and that is assuming you are inside a shielded spacecraft. If anything goes wrong, if your water supply, which doubles as radiation shielding, runs low, the exposure rate jumps by an order of magnitude. You do not die of old age on an interstellar journey. You die of radiation poisoning, alone, in a metal tube, light years from anything that ever knew your name. And we have not even talked about what happens to your bones yet, or your mind, or the fact that the ship you are riding in would need to carry enough fuel, food, water, and spare parts to sustain a closed-loop ecosystem for centuries, or the fact that anything mechanical breaks, or the fact that cosmic radiation damages electronics just as efficiently as it damages cells, or the fact that at the distances we are talking about, communication with Earth becomes effectively impossible. A message sent from Proxima Centauri takes 24 years to arrive. If something goes wrong, if you need help, if you want to tell someone back home that you made it, you send the signal and then you wait. 4 years later, maybe someone hears it. 4 years after that, maybe they respond. By the time you get an answer, the crisis that prompted the message is almost a decade old. You are not exploring, you are disappearing. That is what 1 light year means. It is not an inspirational milestone. It is not a finish line waiting to be crossed by the right team with the right tools. It is a gulf so wide that crossing it stops being a transportation problem and starts being an extinction problem. You do not survive it. Your children do not survive it. Your children's children might, if everything goes perfectly, if the ship holds together, if the ecosystem does not collapse, if a stray rock does not punch through the hull at 100,000 miles per hour and turn the interior into a cloud of shrapnel and frozen blood. We talk about interstellar travel the way we talk about climbing mountains. Hard, yes. Dangerous, sure, but doable. Everest kills people, and we still climb it. The Marianas Trench is hostile, and we still go down. We assume the stars are just the next step on the same ladder. They are not. They are not even on the ladder. They are on a different planet where the ladder does not exist, and the air does not have oxygen, and the ground is made of things that burn you when you touch them. 1 light year is not a distance humans are built to cross. It is a distance that requires you to stop being human in any recognizable sense and become something else, something that can tolerate decades in a box, something that can watch everyone it loves age and die while it drifts, something that does not go insane from isolation or despair or the creeping knowledge that there is no going back. And that is just 1 light year. Most destinations are farther. So when someone says, we just need a better engine, what they are really saying is they have not looked at the map. The map is not encouraging. The map says you are here, and everything interesting is there, and the space in between is so large that the difference between walking and flying is a rounding error. The engine is not the bottleneck. The universe is the bottleneck, and the universe does not negotiate. But let us say, for the sake of argument, that you solve the engine problem. Let us say you build a ship that can reach 10% of light speed, a velocity that would get you to Proxima Centauri in about 40 years. You load it with supplies, you staff it with a crew, you launch. 40 years later, you arrive. Congratulations. You have just discovered that time, the thing you thought was universal, the thing that ticked the same for everyone everywhere, does not. Because the faster you go, the slower your clock runs compared to everyone else's. And by the time you step off the ship, the people you left behind are not 40 years older. They are dead. And the world you returned to, if you bothered to return at all, is not the world you left. It is something new, something that moved on without you. That is where we are going next. You left off standing on the edge of a launch pad, looking at a ship that can supposedly reach 10% of light speed. 40 years to Proxima Centauri. A human lifetime, sure, but achievable. You load the crew, seal the hatch, and light the engine. The ship accelerates. Days pass, weeks, months. You settle into the routine. And then, somewhere in the third year of the journey, you start to notice something strange. Your watch still ticks at the same rate it always has. Your heart still beats 70 times a minute. You age at the pace you have always aged. But the messages coming in from Earth, the ones that take years to arrive because of the distance, start to feel off. The timestamps do not line up. The people writing to you are aging faster than they should, a lot faster. By the time you reach Proxima, step off the ship and look back at the data log, 40 years have passed for you, but Earth has aged by something closer to 41, maybe 42. The discrepancy is small at 10% light speed, but it is there, and if you had gone faster, much faster, the gap would not be small. It would be catastrophic. That is time dilation. And it is not a metaphor. It is not a storytelling device. It is a measurable, reproducible, experimentally confirmed feature of reality that has been tested in particle accelerators, aboard jet planes, and on satellites orbiting the Earth. The faster you move through space, the slower you move through time relative to anyone who is standing still. And the effect is not symmetrical. It is not like two people walking away from each other at the same speed. It is more like one person standing on a platform while the other person rides a train that is on fire and also stretching the fabric of the universe as it moves. When the rider gets off, they are younger than the person who stayed behind, not because they aged slowly in some subjective sense, because less time actually passed for them. Their clocks, their cells, their neurons, all of it ran slower. They did not feel it, but it happened. The man who figured this out was Albert Einstein, and he did it in 1905 while working as a patent clerk in Switzerland. He was 26 years old. He had no access to a laboratory, no team of researchers, no funding. He had a pen, some paper, and a willingness to take two ideas that everyone already agreed on and push them to their logical conclusion. The first idea was that the speed of light is constant. No matter how fast you are moving, no matter what direction you are going, light always moves at the same speed relative to you. 300,000 kilometers per second. Roughly 186,000 miles per second. That number does not change. If you are standing still and you shine a flashlight, the light moves away from you at that speed. If you are on a rocket moving at half the speed of light and you shine a flashlight forward, the light still moves away from you at that same speed. Not faster, the same. That seems wrong. It violates every intuition we have about how motion works. If you are on a train moving at 50 miles per hour and you throw a ball forward at 10 miles per hour, the ball is moving at 60 miles per hour relative to the ground. That is how speeds add, but light does not add. Light does not care how fast you are going. It always moves at 300,000 kilometers per second relative to you. And that fact, that single immovable fact, is what breaks everything else. The second idea Einstein started with was that the laws of physics are the same in all inertial frames. That is a fancy way of saying that if you are moving at a constant speed in a straight line, you cannot tell whether you are moving or standing still without looking outside. There is no experiment you can do inside a closed room that will tell you your absolute speed. You can only measure your speed relative to something else. If you are on a perfectly smooth train moving at a constant velocity and you drop a ball, the ball falls straight down. It does not drift backward. It does not know the train is moving. As far as the ball is concerned, the train is the entire universe, and the train is at rest. Einstein took those two ideas, the constancy of light speed and the equivalence of inertial frames, and he asked what had to be true for both of them to hold at the same time. The answer he got was disturbing. Time and space cannot be absolute. They have to flex. If light always moves at the same speed for everyone, then the only way that works is if moving clocks run slow and moving rulers shrink. Time itself has to dilate, space itself has to contract, and the amount of dilation and contraction depends on how fast you are moving. He published the idea in a paper called On the Electrodynamics of Moving Bodies. The paper was 17 pages long. It had no references. It contained one of the most important equations ever written, though the equation most people know, E equals mc squared, did not actually appear in that paper. It came later. The equation that matters for interstellar travel is different. It is called the Lorentz factor, and it is usually written as gamma equals 1 divided by the square root of 1 minus v squared over c squared. V is your velocity. C is the speed of light. Gamma tells you how much time slows down for you relative to someone who is standing still. Let me say that again in plain language, because the formula does not help if you cannot picture it. Imagine you are on a spaceship moving at some fraction of the speed of light. Back on Earth, someone is sitting in a chair watching a clock. 1 second ticks by on their clock. For you, on the ship, less than 1 second ticks by. How much less depends on your speed. At low speeds, the difference is tiny. At high speeds, the difference is enormous. The Lorentz factor is the number you multiply Earth time by to get ship time. If gamma is 2, that means for every 2 seconds that pass on Earth, only 1 second passes on the ship. If gamma is 10, then for every 10 seconds on Earth, 1 second passes on the ship. The faster you go, the higher gamma gets, and the slower your time moves relative to Earth. At everyday speeds, the effect is invisible. If you get in a car and drive across the country at 70 miles per hour, your clock will run slow compared to someone who stayed home. But the amount of slowdown is so absurdly small that you would need an atomic clock and a lot of patience to measure it. We are talking about nanoseconds over the course of a road trip. You will not notice, your body will not notice, your cells will not notice. Time dilation at car speeds is real, but irrelevant. At orbital speeds, it starts to matter. The International Space Station moves at roughly 17,500 miles per hour. Astronauts who spend 6 months aboard the station age slightly less than people on the ground. The difference is about 0.01 seconds over the course of a year. Still tiny. Still not something you would feel, but measurable. GPS satellites have to account for time dilation, or their positioning data would drift out of sync within hours. The satellites are moving fast enough, and they are far enough from Earth's gravity well, that time runs differently for them than it does for us on the surface. Engineers bake the correction into the software. If they did not, your navigation app would tell you that you are 3 miles away from where you actually are, and the error would grow every day. At a significant fraction of light speed, time dilation stops being a correction and starts being the dominant fact of your existence. Let us say you are on a ship moving at 90% the speed of light. Your Lorentz factor is about 2.3. That means for every 2.3 years that pass on Earth, only 1 year passes for you. You leave Earth in 2030. You travel for 10 years by your own clock. You arrive at your destination in 2040 by your watch. But back on Earth, 23 years have passed. It is 2053. Everyone you knew is older. Some of them are dead. The world has moved on. You did not skip forward in time like a science fiction character stepping into a portal. You just moved so fast that time itself slowed down for you. And when you stopped moving, you found yourself in everyone else's future. Push the speed higher and the effect gets worse. At 95% the speed of light, gamma is about 3.2. 1 year for you is 3.2 years for Earth. At 99%, gamma is 7. 1 year for you, 7 years for Earth. At 99.9%, gamma is 22. 1 year for you, 22 years back home. You can see where this is going. The closer you get to light speed, the more extreme the ratio becomes. At 99.99%, gamma jumps to 70. At 99.999%, it is over 200. You could spend a single year on a ship moving that fast, turn around, come home, and find that 2 centuries have passed on Earth. You would step off the ship into a world where everyone you ever knew has been dead for generations, where the political borders have changed, where the language has drifted, where your entire cultural context has been erased by time. You are not a traveler anymore. You are a refugee from the past. This is not speculation. This is math, verified math. We have tested time dilation at every scale we can access. Particle accelerators routinely push subatomic particles to 99.99% the speed of light and beyond. Those particles are unstable. They decay. They have known half-lives, the time it takes for half of them to fall apart. When you accelerate them to relativistic speeds, their half-lives stretch. They last longer from our perspective because time is running slower for them. A particle that should decay in a microsecond lasts for milliseconds or longer when it is moving fast enough. The effect is not subtle. It is enormous, and it matches Einstein's predictions exactly. In 1971, 2 physicists named Hafeley and Keating put atomic clocks on commercial airplanes, flew them around the world, and compared them to atomic clocks that stayed on the ground. The flying clocks lost time, not much, a few hundred nanoseconds, but they lost it. The experiment was crude by modern standards, but it worked. Time dilation is real. It happens to clocks. It happens to particles. It happens to anything that moves, including people. So what does this mean for an astronaut on an interstellar journey? It means the trip is survivable for them in a way that it is not survivable for anyone else. If you want to send a human to a star system 10 light-years away, and you can accelerate the ship to 99% the speed of light, the journey takes about 10 years from Earth's perspective. But from the astronaut's perspective, the journey takes less than 2 years. They age 2 years. Their body experiences 2 years. Their mind experiences 2 years. They do not feel like they went fast. They feel like the trip was short. And when they arrive, they look out the window and see a star system that is 10 light-years from Earth, and they sent a message home, and that message takes 10 years to arrive, and the response takes another 10 years to come back. By the time they hear from Earth again, 20 years have passed back home, but for the astronaut, only 2 years have passed. They are 18 years younger than they would have been if they had stayed. That sounds like a gift. It is not. It is a severance. Every time you accelerate to relativistic speeds, you cut yourself off from the timeline you left behind. You do not pause your life. You desynchronize it. You step out of the shared flow of time that connects you to everyone you know, and you step into a private timeline that runs slow, and there is no way to step back. Time dilation is not reversible. You cannot go fast, come home and undo the effect. The universe does not let you rewind. Once you have moved through less time than the people around you, that gap is permanent. You are younger, they are older. The distance between you is measured in years, and no amount of time spent together afterward will ever close it. This is the cruel twist. Time dilation makes interstellar travel technically possible for the traveler. You can cross distances that would otherwise take centuries and experience only years or even months of subjective time. But the cost is exile. You lose everyone. Not because they die in some sudden catastrophic way, but because they age out of sync with you. Your parents grow old and die while you are gone. Your children grow up, have children of their own, grow old and die. Your friends move on, your culture changes. The version of Earth you left becomes a historical period, and you come back, if you come back at all, as a ghost, a person out of time, a living anachronism. You are the same age you were when you left, but the world is not. The world is 100 years older, or 200, or 500, depending on how fast you went and how far. There is no way to prepare for that psychologically. Humans are social animals. We define ourselves in relation to other people. We build identities around the communities we belong to, the families we are part of, the cultural moments we share. Strip all of that away, and what is left? You are still you, but the you that existed was a node in a network, and the network is gone. Everyone you loved is gone. Everyone who understood the references you make, the jokes you tell, the music you listen to, the wars you lived through, the presidents you voted for, all of it is gone. You cannot call home, you cannot go back. You cannot even mourn properly, because mourning requires a shared context, and you do not share a context with anyone anymore. You are alone in a way that no human being has ever been alone before, and this is assuming the trip goes well, assuming the ship does not break, assuming you do not get hit by a rock, assuming the life support holds, assuming you stay sane. Because time dilation does not just separate you from Earth, it traps you in a box where time moves slowly and the walls never change and there is nothing to do but wait. A year for you might be 10 years for Earth, but that year still feels like a year. You still experience 365 days. You still wake up, eat, work, sleep, wake up again. The time does not fly by, it crawls. And while it crawls, you know that back home, everything is moving faster. People are living entire lives in the time it takes you to finish one season. Every day you spend on the ship is a week someone else spends on Earth. Every meal you eat is a month they age. You watch your own clock and you do the math, and you realize that by the time you get home, if you get home, no one will be waiting. Ethically, this is a nightmare. How do you justify sending someone on a mission like that? How do you ask another human being to give up their entire social existence for the sake of a scientific goal or a colonization effort or whatever reason you invent to make the trip sound worthwhile? You cannot offer them glory because glory requires an audience, and their audience will be dead. You cannot offer them reunion because there is no one left to reunite with. You cannot offer them a homecoming because home will not exist in any form they recognize. You can offer them survival. You can offer them the experience of seeing something no one else has seen. But you cannot offer them a life, not in the sense that most people mean when they use that word. Some argue that the astronaut volunteers, that they know what they are signing up for, that informed consent makes it acceptable. But consent to what exactly? Consent to become a temporal exile? Consent to lose every human connection they have ever formed? Consent to age slowly while the species moves on without them? That is not a choice. That is a coin flip between two kinds of death. Either you die on the ship, or you survive and discover that everyone you loved died while you were gone. Neither option is good, and calling it voluntary does not make it less brutal. Others argue that time dilation could be an advantage, that we could send young astronauts on missions lasting centuries from Earth's perspective, and those astronauts would only age a few years. We could span the galaxy in subjective time that fits within a human lifespan. That is true. But it is also irrelevant because the astronauts would still be severed from their origins. They would still arrive in a future they did not live through. And more importantly, they would have no way to communicate meaningfully with anyone back home. A message sent from a ship moving at 99% light speed still travels at light speed. If you are 10 light years away, your message takes 10 years to arrive. By the time Earth responds, you are 20 years out of date. The conversation does not flow, it fractures. Each exchange spans decades. You are not talking to people. You are trading monologues with the dead. There is one other thing worth mentioning, and it is the thing that makes time dilation even stranger than it already sounds. The effect is symmetrical in a specific sense. From the astronaut's point of view, Earth is the thing that is moving. Special relativity says there is no preferred reference frame. If you are on a ship moving at 99% the speed of light relative to Earth, then from your perspective, Earth is moving at 99% the speed of light relative to you. And if moving clocks run slow, then Earth's clocks should be running slow from your perspective. So who is actually aging slower? The answer is both, and neither, depending on when you ask. The symmetry only breaks when one of you accelerates. Acceleration is not relative. Acceleration is absolute. You can feel it. Your body knows when you are accelerating, and the person who accelerates is the person who ends up younger. The astronaut accelerates. The Earth does not. So when the astronaut comes home, they are the one who aged less. But during the trip, while both are moving at constant velocity, each sees the other's clock running slow. It is only when they reunite and compare notes that the difference becomes real. This is called the twin paradox, and it is not actually a paradox. It is just deeply weird. One twin stays on Earth. The other twin gets on a ship, accelerates to near light speed, travels to a distant star, turns around, accelerates again, and comes home. The traveling twin ages less. The Earth twin ages more. When they meet again, the traveler is younger, not because of anything magical, because they spent less proper time moving through the universe. Their path through space-time was shorter in a way that has nothing to do with distance and everything to do with the geometry of how time and space fit together. Einstein did not make this up to sound clever. He derived it from two premises that were already accepted by the physics community, and the result was so strange that even he thought it might be wrong. He spent years checking his own work. So did everyone else. They could not find the error, because there was no error. Time dilation is real. It has been measured. It has been confirmed. It is built into the structure of the universe at a level so deep that you cannot escape it by building a better clock or inventing a new theory. It is not a law you can repeal. It is the way time works when you move. And that means every interstellar mission, every attempt to send humans across the light years, comes with a cost that cannot be engineered away. You can build a faster ship, you can improve the shielding, you can solve the radiation problem and the food problem and the fuel problem. But you cannot solve the time problem. You cannot make the clocks match. You cannot keep the travelers synchronized with the world they left behind. The faster they go, the further they drift. And the further they drift, the less human they become in any social or cultural sense. They are still biologically human. But they are no longer part of the species in the way that matters. They are alone, they are unmoored, they are a single point moving through a universe that refuses to wait. So when you think about crossing 1 light year, or 10, or 1,000, do not just think about the distance. Think about the time. Think about what it means to move so fast that your clock stops matching everyone else's. Think about what it costs to become the person who ages slowly while the world ages fast. And then ask yourself whether the stars are worth it. Whether seeing another sun, another planet, another sky is worth losing every person you have ever known and every moment you might have shared with them. Because time dilation does not care about your reasons. It does not care about your dreams. It does not care whether you are brave or curious or desperate. It just runs the numbers. You go fast, time slows down, the gap widens, and everyone you love becomes a memory that belongs to a world you can never return to. That is the relativistic reality. That is the cost of speed. And it is not the worst thing waiting for you out there. Because even if you accept the temporal exile, even if you make peace with the fact that you will never see home again in any form you recognize, you still have to survive the journey itself. And space, the thing you are moving through at a significant fraction of light speed, is not empty. It is full of things, small things, fast things, things that hit like bombs when you are moving fast enough. Space is not empty. That sentence should not be controversial, but for most people it is news. We have been calling it the vacuum of space for so long that the phrase has calcified into a single concept: vacuum, nothing, a void where the air stops and emptiness begins. The cultural image is clean. Space is black, space is silent, space is the absence of everything. Stand at the edge of it, and you look out into a darkness so total that nothing interrupts it except the distant points of stars. That image is wrong. Deeply, fundamentally, dangerously wrong. And if you try to cross interstellar distances while believing it, you will not last long enough to realize your mistake. The region between stars, the place astronomers call the interstellar medium, is not a sterile void. It is a thin soup of matter and energy spread across distances so vast that calling it thin is almost misleading. Roughly 1 hydrogen atom per cubic centimeter on average. That is sparse by any terrestrial standard. The air you are breathing right now contains about 10 to the 19th power molecules per cubic centimeter, 10 billion billion. The interstellar medium is emptier than any vacuum we can create in a laboratory by a factor of trillions. But emptier than a lab vacuum is not the same thing as empty. And when you are moving through that not quite empty space at 10% the speed of light, or 50%, or 90%, every atom you encounter stops being negligible and starts being a problem. Let me put it more clearly. At rest, a hydrogen atom weighs almost nothing, 1.67 times 10 to the negative 27 kilograms. That is a decimal point, followed by 26 zeros, and then a 1. You could hold a trillion of them in your hand and not feel the weight. But mass is only half the equation. The other half is velocity. And velocity, when you square it and multiply it by mass, gives you kinetic energy. That is the energy something carries purely because it is moving. A car moving at 60 miles per hour has kinetic energy. A bullet has more. A meteor entering the atmosphere has vastly more. And a hydrogen atom encountered by a spacecraft moving at 90% the speed of light has enough kinetic energy to punch a hole through metal. This is not an exaggeration. This is physics. The formula is simple. Kinetic energy equals 1/2 times mass times velocity squared. When velocity gets large, truly large, the squared term dominates everything. A hydrogen atom sitting still has no kinetic energy. A hydrogen atom moving at 10 meters per second, which is a brisk jog, has a kinetic energy you could measure in joules, but that you would need scientific notation to write down in a way that matters. A hydrogen atom moving at 10,000 meters per second, which is faster than a rifle bullet, carries enough energy to be detectable if it hit you. A hydrogen atom moving at 10% the speed of light, which is 30,000 kilometers per second, carries roughly the same kinetic energy as a car moving at highway speed. One atom, one single proton, same energy as a 2-ton vehicle doing 70. And that is only at 10% light speed. Push the velocity higher and the numbers get obscene. At 50% the speed of light, a single hydrogen atom hits with the energy of a small bomb. At 90%, it hits with the energy of several pounds of TNT. At 99%, a single proton carries the kinetic energy equivalent of a freight train moving at full speed. And at 99.9%, the kind of speed you would need to make interstellar travel remotely practical from a time dilation standpoint, every hydrogen atom you collide with releases energy comparable to a tactical nuclear weapon. One atom, one proton. A particle so small you cannot see it even with the most powerful microscope ever built, and it hits your ship like a warhead. Now remember that the interstellar medium contains roughly one hydrogen atom per cubic centimeter. That does not sound like much until you do the math on how many cubic centimeters your ship is sweeping through per second. Let us say your ship has a cross-sectional area of 100 square meters, which is modest. That is 10 to the 6th square centimeters. You are moving at 99% the speed of light, which is roughly 3 times 10 to the 10th centimeters per second. Every second, your ship sweeps through a volume of about 3 times 10 to the 16th cubic centimeters. If the interstellar medium has one hydrogen atom per cubic centimeter, that means you are hitting 30 quadrillion hydrogen atoms every second. 30 quadrillion tiny nuclear bombs every second slamming into the front of your spacecraft, not in a single catastrophic impact, in a continuous particle storm that never stops as long as you are moving. The effect is cumulative. Each individual impact might not destroy the ship on its own, but the steady bombardment degrades every surface it touches. The hull erodes, the outer layers vaporize. Atoms are knocked loose, the material heats up, microfractures form, radiation is released, and all of this happens at a rate that scales with your velocity. Go twice as fast, and you do not hit twice as many particles. You hit twice as many particles with 4 times the energy each. The damage does not double, it quadruples. Go 10 times faster, and the damage increases by a factor of 100. The interstellar medium, which looks like nothing when you are standing still, becomes a sandblaster made of atomic buckshot moving at relativistic speeds, and your ship is the surface being sanded away. Then there is the dust. The interstellar medium is not just hydrogen and helium. Roughly 1% of its mass, by most estimates, is solid particles, dust grains. They are tiny, typically a fraction of a micron across, smaller than a bacterium, composed mostly of silicates, carbon, iron, and frozen water mixed with other ices. Astronomers call it interstellar dust, and it sounds harmless because the word dust sounds harmless. Dust is what collects on your shelf. Dust is what you wipe off with a cloth. Dust is annoying but not dangerous. That intuition works on Earth, where dust is sitting still or drifting slowly through the air. It does not work in interstellar space, where your ship is moving at a significant fraction of light speed and every dust grain you hit is moving, from your perspective, at that same speed in the opposite direction. A single dust grain, 1 micron across, weighs roughly 10 to the negative 15 kilograms. That is a millionth of a billionth of a kilogram. Effectively nothing, but at 99% the speed of light. That grain carries kinetic energy equivalent to several kilograms of TNT. It does not bounce off your hull. It does not scratch the paint. It punches through. It vaporizes on impact, releasing a burst of energy so intense that it creates a plasma fireball inside your ship. 1 grain, 1 microscopic speck of cosmic dust, and it produces an explosion that could kill everyone in the compartment it hits. The interstellar medium is not uniformly dense. Some regions are thicker than others. Molecular clouds, the stellar nurseries where new stars are born, can have densities 10,000 times higher than average. If your trajectory takes you through one of those clouds, the impact rate does not go up by a little, it goes up by 4 orders of magnitude. 30 quadrillion hits per second becomes 300 quadrillion. The ship does not slowly erode, it disintegrates. The hull fails. The shielding evaporates. The interior is exposed to vacuum and radiation. Everyone on board dies, not over years or months, but in seconds. And the cloud you flew through was invisible from a distance. Just a slightly darker patch of sky, no warning, no way to avoid it unless you mapped every cubic light year of your route in advance, which you cannot do because interstellar clouds move and change shape and new ones form all the time. Engineering a defense against this is not impossible, but it is expensive in ways that go far beyond money. The most commonly proposed solution is a shield, not a passive sheet of metal which would vaporize instantly under relativistic bombardment, but an active system, something that pushes particles out of the way before they hit. One idea is a magnetic field projected ahead of the ship, strong enough to deflect charged particles like protons and helium nuclei. Cosmic rays are mostly charged, so in principle, a powerful enough magnetic field could sweep them aside, creating a safe corridor for the ship to move through. The problem is scale. To be effective, the field would need to extend for kilometers in front of the ship, maybe tens of kilometers. Generating a magnetic field that strong, that large, and that stable requires enormous amounts of energy. And the energy has to come from somewhere. You need reactors, you need coolant, you need redundant systems in case something fails. And all of that adds mass, which means you need more fuel to accelerate, which adds more mass, which requires even more fuel. The ship grows, the complexity grows, the cost grows, and you still have not solved the dust problem because dust grains are not always charged. A magnetic field does not deflect a neutral particle, it passes right through. Another idea is a sacrificial shield, a thick slab of material positioned ahead of the ship, far enough forward that when particles hit it and explode, the explosion does not damage the ship itself. The shield takes the beating, it erodes. You replace it periodically, or you accept that by the end of the journey it will be mostly gone and hope that the ship behind it is still intact. This works in theory. In practice, you are talking about a shield massing thousands of tons, positioned kilometers ahead of a ship traveling at near light speed. How do you keep it aligned? How do you prevent it from drifting? What happens if the tether breaks? What happens if a dust grain hits the tether? The whole system is a fragile solution to a problem that does not forgive fragility. A third idea is to go around, map the interstellar medium in advance, identify the densest regions, and plot a course that avoids them. This is the safest option. It is also the slowest. Dense regions are not rare, they are everywhere. Avoid all of them, and your route becomes a maze. The shortest path between two stars is a straight line. but the safest path might be 3 times longer. You add years to the journey, decades maybe, and you still cannot avoid everything because some hazards are too small to detect from a distance, and some move into your path after you have already committed to the trajectory. Space is not static. The interstellar medium flows, clouds drift. Shock waves from supernova remnants push walls of gas across the galaxy at thousands of kilometers per second. You cannot predict where everything will be by the time you get there. The fourth option is not to go fast. Stay below 10% the speed of light, and the particle impacts become manageable. At low relativistic speeds, hydrogen atoms hit with the energy of bullets instead of bombs. Dust grains damage the hull, but do not vaporize it. The ship can be armored. The journey becomes survivable from an engineering standpoint. The trade-off is time. At 10% light speed, a trip to Proxima Centauri takes 40 years. A trip to a star 10 light-years away takes a century. A trip to anywhere interesting in the galaxy takes multiple human lifetimes. You are not sending astronauts anymore. You are sending a generational arc. And generational arcs have their own problems, which we will get to later. The point is that slowing down solves the particle problem but reintroduces the time problem, and you cannot solve both at once. There is one more component of the interstellar medium that makes the whole situation worse, and it is the one most people have never heard of: cosmic rays. These are not rays in the way light is a ray. They are particles, high-energy protons and atomic nuclei, mostly hydrogen and helium, moving at speeds close to light speed themselves. Some of them are accelerated by supernova shock waves. Some come from pulsars. Some are flung out by black holes. They cross the galaxy in all directions, and they do not slow down. The typical cosmic ray moves at about 90% the speed of light. That means if your ship is moving at 90% the speed of light in one direction, and a cosmic ray is moving at 90% in the opposite direction, the relative velocity between you and that particle is not 180%. Velocities do not add like that at relativistic speeds. You have to use the relativistic velocity addition formula, and when you do, the result is something close to 99.9% the speed of light. The cosmic ray, from your perspective, is moving almost as fast as light can move, and it carries enough energy to ionize every molecule it touches as it passes through your ship, through your body, through your DNA. Cosmic rays are one of the reasons radiation is such a nightmare for interstellar travel, but they also contribute to the particle problem. A proton moving at 90% light speed relative to the interstellar medium is already carrying enormous kinetic energy. Add your ship's velocity on top of that, and the collision energy spikes even higher. Some cosmic rays are not protons. Some are iron nuclei, which are 26 times heavier. An iron nucleus moving at near light speed and hitting your ship head-on releases enough energy to be visible. It leaves a track. It creates a flash of light inside the hull as it ionizes the air. Astronauts on the International Space Station, which is not moving anywhere near light speed, report seeing flashes when they close their eyes. Those are cosmic rays passing through their eyeballs, triggering the retina as they go. On an interstellar ship moving at relativistic speeds, those flashes would be constant, not occasional, constant. And each one represents a particle carrying enough energy to damage cells, break chemical bonds, and increase the risk of cancer every single time it passes through you. The interstellar medium is not empty. It is a thin, violent, particle-filled storm that spans the entire galaxy. And the faster you move through it, the more violent it becomes. At low speeds, it is a nuisance. At high speeds, it is a minefield. At the speeds required to make interstellar travel practical within a human time frame, it is a continuous existential threat that does not pause, does not weaken, and does not care whether you survive. You are a solid object moving through a diffused cloud of matter at velocities where physics stops distinguishing between a collision and an explosion. Every particle you hit becomes a tiny bomb. Every dust grain becomes a grenade. Every cosmic ray becomes a bullet made of ionized nuclei, moving faster than anything humans have ever built. You cannot see it coming. The particles are too small. The distances are too large. By the time light from an approaching dust grain reaches your senses, the grain has already hit you because you are both moving toward each other at near light speed, and light does not travel infinitely fast. There is no warning system that works at these velocities. There is no time to react. The impact happens, the damage occurs, and you find out afterward by reading the sensors that tell you how much of your hull just evaporated, or how many systems just failed, or how many people just died in the compartment that took a direct hit. This is the interstellar medium. This is the space you have to cross to get to another star, and it is not the empty void you were promised. It is a shooting gallery where the bullets are invisible, the guns never stop firing, and every hit counts. You can engineer your way through it, maybe if you are willing to build a ship the size of a city and accept that parts of it will erode away during the journey, and hope that the critical parts last long enough to get you where you are going. Or you can go slow, stay below the threshold where particles turn into bombs, and accept that the trip will take centuries. Either way, you are not exploring. You are threading a needle through a hurricane while the needle is on fire and the hurricane is made of microscopic shrapnel. And even if you survive the particles, even if your shielding holds and your magnetic deflectors work and your trajectory avoids the densest clouds, you still have to deal with the radiation. The unshielded, continuous, biology-shredding radiation that fills every cubic centimeter of interstellar space and does not stop accumulating dose as long as you are out there. The particles will kill you fast if something goes wrong. The radiation will kill you slowly, even if everything goes right. You survived the particle storm. Every hydrogen atom that should have hit like a bomb somehow missed, or your shielding held, or you got lucky. The magnetic deflectors worked. The sacrificial shield took the beating. The trajectory avoided the densest clouds. You made it through the interstellar medium without the hull evaporating or a dust grain punching through the crew compartment and killing everyone inside. Congratulations, you have cleared one obstacle. Now you get to deal with the next one, and this one does not come at you in bursts. It does not spike when you hit a dense region and fade when you enter a void. It is everywhere, all the time, soaking through the walls of your ship like water through paper, and it is killing you slowly, invisibly, at a rate that accumulates with every hour you spend in deep space. Radiation. Not the kind you get from a microwave or a cell phone tower or the fear-mongering article your aunt shared on social media. Real radiation, ionizing radiation, the kind that strips electrons off atoms as it passes through matter, breaking chemical bonds, shattering molecules, turning the orderly machinery of your cells into a junkyard of damaged parts that do not work anymore. On Earth, you are shielded from most of it. The atmosphere absorbs it. The magnetosphere deflects it. You walk outside, you stand in the sun, and the worst thing that happens is you get a sunburn if you stay out too long. In space, beyond the protective bubble of Earth's magnetic field and atmosphere, the shielding is gone. The radiation does not get filtered, it does not get softened. It comes at you full strength from every direction, all day, every day, and it does not stop. There are two main sources, and both of them are bad. The first is galactic cosmic rays, usually shortened to GCRs. These are high-energy particles, mostly protons, but also helium nuclei and heavier elements, accelerated to near light speed by supernova explosions, pulsars, and other violent events scattered across the galaxy. They have been traveling for millions of years, crossing distances so vast that by the time they reach your ship, they have lost all connection to whatever star or explosion originally flung them into space. They are just particles now, fast particles. Particles carrying so much kinetic energy that when they hit an atom in your body, they do not bounce off. They smash through, ionizing everything in their path, leaving a trail of broken molecules behind them like a bullet through tissue. GCRs are not rare, they are constant. At any given moment, billions of them are passing through the space your ship occupies. Most of them pass through harmlessly because space, even inside a ship, is mostly empty at the atomic level. Your body is mostly empty. The atoms that make up your cells are tiny, and the space between them is relatively vast. A cosmic ray can pass through you without hitting anything important. But not always. Sometimes it hits a water molecule and splits it into reactive fragments that go on to damage nearby proteins. Sometimes it hits the DNA in the nucleus of a cell and breaks one of the strands, forcing the cell to attempt a repair that might introduce errors. Sometimes it hits a critical protein in a neuron and disrupts the electrical signaling in your brain. And because there are billions of these particles passing through you constantly, the hits add up. The second source is solar particle events, or SPEs. These are bursts of radiation released by the sun during solar flares and coronal mass ejections. When the sun's magnetic field twists and reconnects in a violent way, it flings a cloud of charged particles out into space at speeds approaching a significant fraction of light speed. If you happen to be in the path of that cloud, you get hit with a dose of radiation that can spike to dangerous levels in a matter of hours. On Earth, the atmosphere and magnetosphere absorb most of it. Astronauts on the International Space Station, which orbits within Earth's magnetosphere, get some protection. Not perfect protection, but enough that a solar flare is a concern rather than a death sentence. In deep space, there is no magnetosphere, there is no atmosphere. The particles hit your ship at full strength, and if you do not have enough shielding, or if you are caught outside during a repair when the event occurs, the dose you receive can be lethal. SPEs are unpredictable. The sun goes through an 11-year cycle of activity, with solar maximum being the period when flares and coronal mass ejections are most common. But even during solar minimum, flares can happen. And even a modest flare, the kind that would barely make the news if it happened today, can release enough radiation to give an unprotected astronaut in deep space acute radiation sickness within hours. Nausea, vomiting, fatigue, then hair loss, bleeding, immune collapse, and death. Not over years, over days or weeks. SPAs are the sniper shots. GCRs are the constant drizzle. Both will kill you. One does it fast. The other does it slow. And you have to prepare for both. When a high-energy particle passes through your body, it does not just break one thing and stop. It creates a cascade. The initial hit ionizes an atom, which means it knocks an electron loose. That free electron, now carrying energy of its own, goes on to ionize other atoms nearby. Those secondary ionizations create more free radicals, reactive molecules that do not exist in normal chemistry because they are too unstable. Free radicals attack anything they touch. They oxidize proteins, making them non-functional. They damage lipids in cell membranes, making the membranes leaky. They break DNA strands, which is the worst possible outcome because DNA is the instruction manual for every process in your body. Damage the manual and the cell either dies, stops dividing, or starts dividing incorrectly. The third option is cancer. Your body has repair mechanisms. Cells can fix broken DNA strands most of the time. Enzymes patrol the genome, looking for errors and snipping them out. But the repair process is not perfect. Sometimes the fix introduces a mutation. Sometimes the repair machinery itself gets damaged by radiation before it can do its job. And sometimes the damage is so extensive that the cell gives up and triggers apoptosis, programmed cell death. That is actually the safe option. A dead cell is better than a mutated cell that keeps dividing. But if too many cells die at once, the tissue they belong to stops functioning. Your bone marrow, which produces blood cells, is particularly vulnerable. Your intestinal lining, which replaces itself constantly, is vulnerable. Your brain, which does not replace neurons, is vulnerable in a different way. Radiation does not kill neurons outright in most cases. It disrupts the signaling. It damages the myelin sheaths that insulate nerve fibers. It causes inflammation, and the cumulative effect, over months or years of exposure, is cognitive decline, memory problems, slower reaction times, difficulty concentrating. The same symptoms you would associate with aging or neurodegenerative disease, but compressed into a much shorter time frame. NASA has studied this extensively, not because they are planning an interstellar mission, but because they are planning missions to Mars, and Mars is far enough from Earth that radiation becomes a serious concern. The numbers they have published are not encouraging. A round trip to Mars, lasting roughly 2 to 3 years depending on the trajectory, would expose astronauts to a cumulative radiation dose of somewhere between 300 and 450 milligray, assuming typical shielding. A milligray is a unit of absorbed dose. It measures how much energy the radiation deposits in your tissue. For context, a chest X-ray delivers about 0.1 milligray. A full-body CT scan is around 10 milligray. The trip to Mars, even with shielding, would be equivalent to several thousand chest X-rays or dozens of CT scans. And that is just to Mars, which is a few light minutes away. An interstellar journey, spanning years or decades, would rack up doses that make the Mars numbers look trivial. Other estimates break the exposure down differently. One frequently cited figure is that deep space delivers roughly 1 to 2 millisieverts per day. A millisievert is a unit of dose equivalent, which accounts for the type of radiation and how damaging it is to biological tissue. For practical purposes, 1 millisievert is roughly equivalent to 10 chest X-rays. That means an astronaut in deep space, outside Earth's protective bubble, is receiving the equivalent of 10 to 20 chest X-rays every single day. Multiply that out over a year, and you are looking at somewhere between 3,600 and 7,300 chest X-rays annually. Over a decade, the number climbs into the tens of thousands. At that dose level, the question is not whether you will develop cancer. The question is how many cancers you will develop, and whether any of them will kill you before something else does. The biological effects are not limited to cancer. Radiation damages the cardiovascular system. The European Space Agency has noted that prolonged exposure raises the risk of cardiovascular disease later in life, possibly due to inflammation and damage to the endothelial cells that line blood vessels. The nervous system is also affected. NASA has stated plainly that space radiation may impair cognitive function and performance during missions. Animal studies, conducted using realistic low-dose rate exposures similar to what astronauts would experience in deep space, have shown measurable deficits in learning and memory. The animals were not blasted with a single high dose. They were exposed to a steady trickle of radiation over time, the way a human crew would be, and even that low chronic exposure was enough to produce brain damage. This is not speculative, this is data. Researchers have put rodents in radiation fields designed to simulate galactic cosmic rays, exposed them for weeks or months, and then tested their ability to navigate mazes, recognize objects, and remember spatial cues. The irradiated animals performed worse. Not slightly worse. Measurably, statistically significantly worse. Their neurons showed signs of damage. Their brains had elevated levels of inflammation. And this was at doses far lower than what a human would receive on a multi-year interstellar journey. Scale the exposure up to match an actual mission, and the cognitive effects would be severe. You would still be conscious. You would still be able to perform basic tasks, but your ability to think clearly, to solve problems, to react quickly in an emergency, would degrade over time, and there is no recovery. Once the neurons are damaged, they do not regenerate. The decline is permanent. Then there is the issue of secondary radiation. When a high-energy cosmic ray, usually a proton or a heavy nucleus, slams into the hull of your spacecraft or into the shielding material you have placed around the crew compartment, it does not just stop, it interacts. It breaks apart the nuclei of the atoms in the shielding, producing a spray of secondary particles. Protons, neutrons, pions, heavier fragments, all of them carrying energy and all of them capable of causing further ionization as they scatter through the ship. In some cases, secondary radiation can make up a significant fraction of the total dose the crew receives. Thick shielding helps block some of the primary particles, but it also increases the production of secondaries. There is a sweet spot, a thickness where the shielding reduces the overall dose as much as possible without creating too many secondary particles. But even at that optimal thickness, the dose is still high. You are not eliminating the radiation, you are managing it. And management, in this context, means accepting that everyone on board will be slowly poisoned by ionizing particles for the duration of the journey. Some materials are better than others. Hydrogen-rich materials, like water or polyethylene, are more effective per unit mass than metals like aluminum or steel. The reason is that hydrogen nuclei, which are just single protons, are good at absorbing energy from incoming particles without producing as many dangerous secondaries. Water has the added advantage that you need it anyway. Surround the crew compartment with tanks of water, and you get both radiation shielding and a supply of drinking water. The problem is mass. Water is heavy. If you want enough of it to provide meaningful shielding for a crew of 10 people on a journey lasting decades, you are talking about hundreds of tons. And every ton of shielding is a ton of mass that has to be accelerated, which requires more fuel, which adds more mass, which requires even more fuel. The rocket equation, which governs how much propellant you need to reach a given velocity, is exponential. Adding shielding does not just make the ship heavier, it makes the entire mission exponentially more expensive in terms of energy and resources. Another approach is active shielding. Instead of using passive material to absorb radiation, you generate a magnetic field around the ship strong enough to deflect charged particles before they reach the crew. This is essentially what Earth's magnetosphere does, and in principle, it could work for a spacecraft. The problem is scale. Earth's magnetosphere is powered by a dynamo deep inside the planet, driven by the motion of molten iron in the outer core. The energy output is enormous. A spacecraft does not have a molten core. It has reactors, and those reactors would need to generate a field strong enough to deflect particles moving at near light speed across a volume large enough to encompass the entire ship. The power requirements are staggering, and even if you could generate the field, it only works on charged particles. Neutrons, which have no charge, pass right through. So do gamma rays. You would still need passive shielding to deal with those, which brings you back to the mass problem. A more speculative idea involves using plasma, ionized gas, to create a buffer zone around the ship. The plasma would absorb some of the incoming radiation and scatter the rest, reducing the dose that reaches the crew. This is still in the research phase. No one has built a working prototype. No one knows whether it would hold together under the conditions of interstellar space. And even if it works, it does not eliminate the problem. It reduces it. The crew still gets irradiated, just less. The truth is that with current technology, and with any plausible near-term technology, there is no way to fully shield a crew from the radiation environment of deep space. You can reduce the dose, you can optimize the shielding, you can time the mission to avoid solar maximum. You can build the ship with materials that minimize secondary particle production, but you cannot bring the dose down to safe levels. Not for a journey lasting years or decades. The radiation is always there. It is always penetrating, and it is always damaging your body faster than your body can repair itself. To give you a sense of the numbers in plain terms, let us say you are on a ship traveling to a star 10 light years away. You are moving at 10% the speed of light, so the trip takes a century from Earth's perspective. Time dilation is minimal at that speed, so you experience close to a full century as well. Let us also assume you have good shielding, the kind that reduces the dose to roughly 1 millisievert per day, which is optimistic. Over the course of 100 years, that is 36,500 millisieverts, or 36.5 sieverts. For comparison, acute radiation sickness begins at around 1 sievert, delivered over a short time. 5 sieverts in a short period is lethal. 36 sieverts spread over a century does not kill you outright, but it destroys your health. Your cancer risk skyrockets. Your cardiovascular system deteriorates. Your brain function declines. Your immune system weakens. By the time you reach your destination, if you reach it, you are a walking collection of radiation-induced diseases, and that is with good shielding. Without it, the dose climbs higher, the damage accelerates. And the question stops being whether you survive the journey and starts being how long you last before the cumulative effects kill you. NASA has looked at the cancer risk specifically. Their estimates suggest that a Mars mission would increase an astronaut's lifetime cancer risk by somewhere between 1 and 5%, depending on age, sex, and shielding. That might sound acceptable for a short mission, but scale it up. An interstellar journey lasting decades or a century would increase the risk by double-digit percentages, maybe more. At some point, the question is not whether you will get cancer, it is which organ gets it first. Then there is the fact that radiation dose is cumulative over your lifetime. Every chest X-ray you have ever had, every CT scan, every background exposure from natural sources like radon or cosmic rays at high altitude, all of it adds up. An astronaut selected for an interstellar mission would start with some baseline dose already accumulated over their lifetime on Earth. The journey adds to that, and there is no reset button. Your body does not forget. The mutations stay, the damaged cells stay, the inflammatory markers stay. You carry the effects with you for the rest of your life, however long that turns out to be. One NASA source put it simply: 1 millisievert of ionizing radiation is about 10 chest X-rays. Deep space gives you 1 to 2 millisieverts per day. Do the math. You are getting 10 to 20 chest X-rays every single day, not over the course of a medical career, every day, for years. The European Space Agency has said that prolonged radiation exposure on interplanetary journeys can raise the risk of cancer or cardiovascular disease later in life, and that the nervous system also seems sensitive. NASA echoed that, noting that space radiation may affect the central nervous system, causing cognitive or performance impairments during missions. These are not alarmist statements. These are conclusions drawn from decades of research, animal studies, and data collected from astronauts who have spent time in low Earth orbit, where the radiation environment is far gentler than deep space. And here is the part that makes it worse. You cannot see radiation, you cannot hear it, you cannot feel it. It does not hurt when it hits you. There is no immediate feedback to tell you that your DNA is being shredded, that your neurons are being damaged, that your bone marrow is struggling to keep up with the demand for new blood cells. You go about your day, you eat, you work, you sleep, and the whole time, invisible particles are passing through your body, breaking things at the molecular level, and you have no idea it is happening until months or years later when the symptoms start to show. The fatigue, the headaches, the memory lapses, the blood tests that come back abnormal. By then, the damage is done. You cannot undo it. You cannot reverse it. You can only manage it, and management, in this case, means watching yourself slowly fall apart while the mission continues. There is one other thing worth mentioning. Radiation does not affect everyone equally. Age matters. Younger people, whose cells are dividing more rapidly, are more vulnerable to radiation-induced mutations. Sex matters. Women have a higher baseline cancer risk from radiation exposure than men, partly because breast and ovarian tissue are more radiosensitive. Genetics matter. Some people have more efficient DNA repair mechanisms than others, but none of that changes the fundamental equation. Everyone on the ship gets irradiated. Everyone accumulates dose. Everyone faces elevated risks of cancer, cardiovascular disease, and cognitive decline. The only question is who gets sick first and how bad it gets before the journey ends. So what does this mean for an interstellar mission? It means you cannot send people without accepting that you are sentencing them to a lifetime of radiation-induced health problems. It means the crew you select has to understand that they will spend the rest of their lives dealing with the consequences of the exposure, and that there is no cure, no treatment that will undo the damage. It means you are asking people to volunteer for a mission where the environment itself is toxic, where every day spent in transit shortens their lifespan, where the goal of reaching another star comes at the cost of their long-term health. And even if they agree, even if they sign the waiver and accept the risk, you still have to deal with the logistics, medical supplies, diagnostic equipment, drugs to manage the side effects, trained personnel who can recognize the symptoms of radiation sickness and treat them as best they can with limited resources, a plan for what to do if someone develops a radiation-induced cancer mid-flight, surgery in zero gravity with no backup, chemotherapy with a limited supply of drugs, palliative care for crew members who are dying because the cumulative dose finally caught up with them, and all of this happening in a closed environment where everyone else is watching, knowing that they are next. The radiation problem does not have a solution, not with current technology, not with anything on the drawing board. You can mitigate it, you can reduce it, but you cannot eliminate it. And the longer the journey, the worse it gets. 1 light year is 5.88 trillion miles. Cross that distance at any speed that makes the trip survivable in terms of time, and you are exposing the crew to radiation levels that guarantee long-term health decline. The dose is cumulative. The damage is progressive, and the universe does not care whether you make it. The particle storm can destroy your ship in seconds if you are unlucky. The radiation destroys your body slowly, over years, whether you are lucky or not. Both are consequences of moving through a space that is not empty and not safe. And both are unavoidable if you insist on crossing the distance between stars. We are not built for this. Our cells, our DNA, our neurons, none of it evolved to tolerate the kind of radiation environment you find in deep space. We evolved on a planet with an atmosphere and a magnetic field and a star that sits far enough away that its radiation reaches us filtered and softened. Strip away that protection and we fall apart. But even if you solve the particle problem, and even if you accept the radiation poisoning as an unavoidable cost, you still have to deal with the fact that your body is not designed to function in the absence of gravity, and that absence does not wait politely until you land. It starts the moment you leave Earth, and by the time you reach your destination, assuming you survive the trip, your bones will be brittle, your muscles will be atrophied, and your cardiovascular system will be so deconditioned that standing up might kill you. You accepted the radiation. You made peace with the fact that invisible particles would be shredding your DNA every day for the rest of the journey, that your cancer risk would climb into double digits, that your brain would slowly lose function and there was nothing you could do to stop it. You strapped yourself into the ship knowing all of that, and maybe you thought that was the worst of it. The radiation, the particle impacts, the isolation, those are the obvious dangers, the ones that sound dramatic, the ones people warn you about. But there is another threat, quieter and slower, that starts the moment you leave Earth's gravity well and does not stop until you return. And by the time you notice it, the damage is already catastrophic. Your bones are dissolving, not metaphorically, not in some poetic sense, literally. Month by month, your skeleton is losing mass, becoming lighter, more porous, more brittle, and there is nothing you can do to stop it, because the thing that keeps your bones strong is the one thing you do not have anymore: gravity. On Earth, gravity is so constant that you forget it exists. You wake up, you stand, you walk, you sit. Every movement you make, every step you take, requires you to push against the pull of the planet beneath your feet. Your muscles contract to hold you upright. Your bones bear the load of your body weight. And that load, that constant mechanical stress, is what keeps your skeleton dense. Bone is not static. It is living tissue, constantly being broken down and rebuilt in a process called remodeling. Cells called osteoclasts chew up old bone. Cells called osteoblasts lay down new bone. In a healthy body under normal gravity, the two processes balance. You lose bone, you gain bone, and the net result is a skeleton that stays roughly the same density year after year. But that balance depends on load. Your bones respond to stress. When you walk, when you run, when you lift something heavy, the mechanical force traveling through your skeleton sends a signal to the osteoblasts that says, "We need to keep this structure strong." The osteoblasts respond by building more bone. Remove the load and the signal disappears. The osteoblasts slow down, the osteoclasts keep working, and the balance tips. You start losing more bone than you build. Over time, the skeleton becomes weaker, lighter, less capable of bearing weight. On Earth, this happens to people who are bedridden for long periods, to people who are paralyzed and cannot walk, to people who spend months in a cast with a limb immobilized. The bone in the affected area wastes away because it is not being used. Doctors call it disuse osteoporosis. Astronauts call it something else. They call it one of the most serious unsolved problems in long-duration spaceflight. The numbers are not subtle. Studies going back to the Skylab missions in the 1970s have consistently shown that astronauts lose roughly 1 to 2% of their bone mineral density per month in microgravity. 1 to 2% per month. That does not sound like much until you start running the timeline forward. 6 months in space, the length of a typical rotation on the International Space Station, and you have lost 6 to 12% of your bone density in weight-bearing regions like the hips, spine, and legs. A year in space, and you are looking at 12 to 24%. 2 years, and the loss climbs into the range where your bones are measurably weaker than they were when you left. And if you stay longer, if you spend a decade in microgravity on an interstellar journey, the cumulative loss becomes catastrophic. You are not talking about a weakened skeleton anymore. You are talking about bones so fragile that a fall, a sudden movement, a moment of clumsiness could result in a fracture. And you are in a ship, light years from Earth, with no hospital, no surgeon, no way to fix a broken bone properly. You splint it, you hope it heals, and you accept that it probably will not heal correctly because the bone itself does not have the density to support proper healing. The loss is not evenly distributed. Weight-bearing bones, the ones that normally carry the load of your body, are hit the hardest. The pelvis, the femur, the spine, the tibia, these are the bones that do the work when you stand and walk. In microgravity, they do not work. You float, you push off walls, you move with your arms as much as your legs. The bones in your lower body stop experiencing the constant compressive forces they evolved to handle, and they waste away faster than bones anywhere else in the body. Your arms, by contrast, lose much less. They are not weight-bearing bones. They do not rely on gravity to stay strong. So while your legs are turning into brittle sticks, your arms remain relatively intact. The result is a body that becomes lopsided, asymmetric, weaker in the exact places where you need strength the most. And here is the part that makes it worse. The bone you lose does not just vanish into nothing. It goes somewhere. The calcium and phosphorus that used to be locked in your skeleton get released into your bloodstream. Your kidneys filter it out and dump it into your urine. Astronauts on the ISS produce urine with elevated calcium levels, a condition that increases the risk of kidney stones. Kidney stones in space are not just painful, they are dangerous. You cannot go to an emergency room. You cannot get imaging. You cannot have a procedure to break up the stone. You ride it out, and you hope it passes, and if it does not, if it blocks a ureter and causes an infection or severe pain, you are in trouble. And the whole time this is happening, your bones are still losing mass. The calcium keeps leaking. The risk keeps climbing. NASA has known about this since Skylab. The first long-duration American space missions, back in the early 1970s, produced data showing that astronauts were losing bone at a rate of about 1 to 1.5% per month. That was 50 years ago. Since then, the agency has spent decades researching countermeasures, testing exercise protocols, refining equipment, analyzing nutrition. The astronauts on the ISS work out for 2 hours a day, every day, using resistance machines designed to simulate the kind of loading your bones would experience on Earth. They lift weights. They run on treadmills with harnesses that pull them down against the platform to simulate body weight. They do squats, deadlifts, leg presses, and it helps. The exercise slows the bone loss. It does not stop it. Even with the most aggressive countermeasures available, astronauts still lose bone. The rate is reduced, maybe cut in half, but the loss continues. And when they return to Earth, it takes months or years to regain what they lost. Some never fully recover. That is a 6-month mission. Now imagine a mission lasting years, a decade, a century. The exercise protocols we have now were designed for short stays. They were optimized for crews spending a few months on the ISS and then coming home. No one has tested whether those protocols work for multi-year missions because no one has flown a multi-year mission in deep space. We are extrapolating. We are guessing. And the guess is not encouraging. If bone loss continues at even half the rate it does without exercise, a 10-year mission still results in cumulative losses in the range of 30 to 60% in weight-bearing bones. At that point, you are not just weak, you are crippled. Your skeleton cannot support your body weight under normal gravity. If you ever return to a planet, you will not be able to walk, you will not be able to stand. You will spend the rest of your life in a wheelchair because your bones cannot bear the load they were designed to bear, and that is assuming the ship has gravity at the destination. If you are traveling to another star system and you arrive at a space station or a habitat in orbit rather than a planetary surface, you might stay in microgravity indefinitely, in which case the bone loss does not stop. It just keeps going. Your skeleton keeps dissolving, and there is no reason to think the process ever bottoms out at some safe minimum. The bones keep losing density as long as the load is absent. Eventually, they become so weak that even the minor forces you experience in microgravity, pushing off a wall, catching yourself during a sudden maneuver, could be enough to break them. Then there is the muscle problem. Bone loss is slow and silent. Muscle loss is faster and more obvious. Within the first 5 to 11 days of microgravity exposure, astronauts begin to lose muscle mass. The muscles that atrophy fastest are the postural muscles, the ones in your lower body that work constantly on Earth to keep you upright. Your calves, your thighs, your glutes, these muscles do not have to work in microgravity. You do not stand. You do not walk. You float, and floating requires almost no effort. So the muscles shrink. Studies have shown that the calf muscle, in particular, shows the most prominent loss. After a few months in space, your legs look visibly thinner. The muscle fibers themselves change. Fast twitch fibers, the ones used for quick, powerful movements, convert to slow twitch fibers or atrophy entirely. The muscles lose strength, lose volume, lose function. And just like with bone, exercise helps but does not prevent the loss. You can work out 2 hours a day and still watch your legs waste away because the exercise, no matter how intense, does not replicate the constant low-level activity your muscles experience on Earth just from existing in gravity. The cardiovascular system falls apart too. On Earth, your heart has to pump blood upward against gravity to reach your brain. It works harder when you stand than when you lie down. In microgravity, that distinction disappears. There is no up or down. The heart does not have to work as hard to move blood around. And because it does not work as hard, it weakens. The walls of the heart muscle become thinner. The chambers shrink. The overall cardiac output decreases. Astronauts returning from space often experience orthostatic intolerance, which is a fancy way of saying they cannot stand up without feeling faint. Their cardiovascular systems have deconditioned so much that the simple act of standing, which requires the heart to pump blood upward against gravity again, is too much. They get dizzy, their heart rate spikes, their blood pressure drops. They have to sit down. And this is after 6 months. Scale it up to years, and the deconditioning becomes severe. You would not be able to tolerate gravity at all without a long, painful reconditioning process, assuming your heart could recover in the first place. There is also a fluid shift. On Earth, gravity pulls blood and other fluids toward your lower body. Your legs swell slightly over the course of a day. In microgravity, fluids redistribute. They move upward into your chest and head. Astronauts report feeling congested, like they have a head cold that never goes away. Their faces look puffy. Their legs, by contrast, look thinner because the fluid has moved elsewhere. The body interprets this fluid shift as an excess of blood volume and responds by reducing the total volume. You urinate more, you lose water, your blood volume drops, and when you return to gravity, you do not have enough blood to go around. Your heart, already weakened, now has to work with less fluid, and the combination of low blood volume and a deconditioned heart makes standing up dangerous. Some astronauts faint. Others experience severe dizziness for days or weeks until their bodies readapt. The autonomic nervous system, the part of your nervous system that controls involuntary functions like heart rate and blood pressure, also changes in microgravity. It stops responding as quickly to changes in posture because there are no changes in posture. You do not go from sitting to standing. You are always in the same neutral floating position. So the reflexes that normally adjust your heart rate and blood vessel constriction when you stand up become sluggish, and when you return to gravity, those reflexes do not work properly anymore. Your body cannot compensate fast enough. Your blood pressure drops. Your brain does not get enough oxygen. You pass out. All of this, the bone loss, the muscle atrophy, the cardiovascular deconditioning, the fluid shifts, the autonomic dysfunction, all of it is happening simultaneously, and all of it is cumulative. The longer you stay in microgravity, the worse it gets. There is no plateau. There is no point where the body adapts and stops deteriorating. The deterioration continues as long as the gravity is absent. One review published in Frontiers described the cardiovascular changes with a single blunt sentence. The price of this adaptation is rapid cardiovascular deconditioning. Another review summarized the bone loss just as plainly. Exposure to conditions of microgravity causes 1 to 2% bone loss per month in astronauts. These are not projections. These are measured effects from real missions. So what do you do about it? The current answer is exercise. Resistance training to stress the bones and muscles, treadmills to simulate walking and running, cycling machines to work the legs. 2 hours a day, every day, for the duration of the mission. And it helps. It reduces the rate of loss. But it does not eliminate it, and more importantly, it might not scale. The exercise protocols we use now were developed for missions lasting months, not years or decades. No one knows whether you can maintain bone and muscle health over a 10-year mission just by working out 2 hours a day. The suspicion, based on the data we have, is that you cannot. The loss continues. It slows, but it does not stop. And over time, the cumulative effect becomes too large to ignore. There is also the practical problem that exercise in space is hard. Not just physically hard, but logistically hard. The equipment takes up space. It requires power. It requires maintenance. The resistance machines use vacuum cylinders and flywheels that wear out over time. The treadmills vibrate, and those vibrations travel through the structure of the ship or station, creating noise and potentially damaging sensitive equipment. The harnesses that pull you down onto the treadmill are uncomfortable. They chafe, they cause bruising. And after 2 hours of exercise in microgravity, you are exhausted in a way that feels different from exhaustion on Earth, because your body is not designed to work this way. You are fighting against resistance without the stabilizing influence of gravity, and every movement feels awkward, unnatural, inefficient. And here is the thing that makes it even more frustrating. You can do everything right. You can follow the exercise protocol perfectly. You can eat the right diet, Take the calcium supplements, do the strength training, and you will still lose bone, you will still lose muscle, because exercise is a mitigation, not a solution. It slows the damage, it does not prevent it. The only thing that actually prevents bone and muscle loss in the long term is gravity, real gravity. Constant, unrelenting, 1 g of acceleration pulling you toward the ground every second of every day. Without that, the body falls apart. Slowly at first, then faster, then catastrophically. So the obvious answer, the one that keeps coming up in every discussion of long-duration spaceflight, is artificial gravity. If microgravity is the problem, then create gravity, spin the ship. Use centripetal force to push the crew outward against the walls of a rotating habitat, creating an acceleration that mimics gravity. The concept is old. It shows up in science fiction as early as the 1920s. Konstantin Tsiolkovsky, one of the founding figures of astronautics, described it in the late 19th century. The math works. Spin a cylinder or a ring at the right speed, and the people inside experience a force pushing them toward the outer wall. That force feels like gravity. It stresses the bones, it loads the muscles, it keeps the cardiovascular system working. In principle, artificial gravity solves the entire problem. In practice, it is enormously complicated. First, you need a structure large enough that the rotation does not make people sick. If the radius is too small, the difference in centripetal acceleration between your head and your feet becomes noticeable. Your feet feel heavier than your head. The gradient is steep. And the Coriolis effect, the apparent force you feel when you move in a rotating reference frame, becomes strong enough to cause nausea and disorientation. Walk in one direction and you feel pushed sideways. Turn your head and the room seems to tilt. The human body can adapt to some degree, but there are limits. Most studies suggest that a radius of at least 10 meters, maybe 20, is necessary to keep the Coriolis effect tolerable. And a 20-meter radius means a structure 40 meters across. That is not a small spacecraft. That is a large rotating habitat, and building something that size, launching it into space, and spinning it up without tearing itself apart requires engineering on a scale we have never attempted. Second, you need to spin it fast enough to generate 1 g of acceleration at the outer rim. The formula is simple. The centripetal acceleration equals the radius times the angular velocity squared. To get 1 g at a radius of 20 meters, you need to spin the structure at about 2 revolutions per minute. That does not sound fast, but for a structure that large it is. The outer rim is moving at roughly 9 meters per second. Any asymmetry in the mass distribution, any imbalance, creates vibrations that grow over time. The structure shakes itself apart unless you balance it perfectly and maintain that balance as the crew moves around inside. Third, you have the problem of transition. If the crew spends time in the rotating section to maintain their health and then has to move to a non-rotating section for other tasks, they have to deal with the disorientation of moving between different reference frames. Climb from the outer rim toward the center, and the artificial gravity decreases. At the hub, where the rotation axis is, there is no gravity at all. You are back in microgravity. Your body has to adapt every time you move between sections. Some people handle that well, others do not. And fourth, there is cost. Building a rotating habitat large enough to be comfortable and strong enough to withstand the stresses of rotation adds enormous mass to the ship. Mass that has to be accelerated, mass that requires fuel, mass that makes the entire mission more expensive and more difficult to launch. For a short interplanetary mission, artificial gravity might not be worth the cost. For an interstellar mission lasting decades, it might be the only option. But that option requires building a ship on a scale that no space agency has ever seriously funded. So where does that leave us? The truth is that with current technology, we cannot send people on a multi-year interstellar journey without accepting that their bodies will deteriorate. The bones will weaken, the muscles will atrophy, the heart will decondition. The astronauts will arrive, if they arrive, in worse shape than when they left. And if the destination does not have gravity, if it is a space station or an orbital habitat, the deterioration continues. There is no recovery. There is no getting better. The body just keeps breaking down until something fails. You can engineer around some of this. You can build better exercise equipment. You can refine the protocols. You can research pharmaceuticals that slow bone loss, drugs that mimic the effects of mechanical loading. Some of that research is happening now. Bisphosphonates, the drugs used to treat osteoporosis on Earth, have been tested on astronauts with mixed results. They slow bone loss, but they do not stop it, and they come with side effects: jaw necrosis, kidney damage, gastrointestinal problems. Over a long mission, the cumulative effects of taking those drugs might be worse than the bone loss they are meant to prevent. Or you bite the bullet and build the rotating habitat. You accept the cost, the complexity, the engineering challenges, and you spin the ship. You give the crew a place where they can live under artificial gravity for most of the journey, maintaining their bone density, their muscle mass, their cardiovascular health. It is possible. It is just expensive. And expensive, in the context of interstellar travel, means prohibitively so unless someone decides that getting humans to another star is worth the investment. But even if you solve the gravity problem, even if you build the rotating habitat, and the crew arrives at the destination with their skeletons intact and their muscles strong, you still have not solved the other problem, the one that does not show up on a bone scan or a cardiovascular stress test. The one that lives inside your head and gets worse the longer you are isolated from everything and everyone you have ever known. The psychological cost of spending years or decades in a metal tube with the same small group of people, cut off from Earth, cut off from real-time communication, cut off from any possibility of escape or rescue. Your body might survive the journey, your mind might not. You solved the gravity problem. You built the rotating habitat, spun the ship up to 1G, gave the crew a place where their bones could stay dense and their muscles could stay strong. You worked out the engineering, balanced the mass, dealt with the Coriolis effect, and accepted the cost. The structure holds, the systems work, the bodies inside remain functional. Congratulations. You have kept the crew physically intact. Now explain to them why, 3 years into a 40-year journey, they want to die. Not because they are sick, not because something broke, not because the radiation finally caught up with them or a dust grain punched through the hull. They want to die because they are alone in a way no human being has ever been alone before, and the loneliness is not poetic. It is not the kind of solitude you experience on a mountaintop or in a desert where you can still see the sky and know that civilization is a few days' walk away. It is the kind of isolation that comes from being sealed in a metal tube with the same 5 people for years, floating through a void so vast that light from Earth takes hours to reach you, knowing that no one is coming, that no help exists, that if something goes wrong you die in the dark and your body drifts forever. That kind of isolation does not build character, it breaks minds. NASA knows this. They have known it since the beginning. Isolation and confinement are listed as one of the 5 major hazards of human spaceflight, right alongside radiation and distance from Earth. Not a minor inconvenience, a hazard, a thing that kills missions and endangers lives. The agency has spent decades studying what happens to people when you lock them in small spaces far from home for long periods of time, and the results are consistent. People suffer, their mood deteriorates, their cognition slips, their ability to work together fractures, and the longer the isolation lasts, the worse it gets. The psychological effects show up fast. Anxiety is usually first. It starts within days or weeks of confinement. You are in a new environment, unfamiliar, unnatural, and your brain recognizes the wrongness of it, even if you do not consciously acknowledge it. You are not supposed to be here. You are a terrestrial organism. You evolved to walk on solid ground under open sky. You did not evolve to float in a can with recycled air and artificial lighting that never quite looks like sunlight. Your nervous system knows that. It responds with a low-level background hum of unease that does not go away. Some people adapt, others do not. The ones who do not spend their days fighting a vague sense of dread that has no specific cause and no solution. Then comes the boredom. This takes longer to develop, usually a few months in. The initial novelty of being in space wears off. The routines become repetitive. Wake up, eat, work, exercise, eat, work, sleep, repeat. Every day the same. The environment does not change. The view outside is black. The people around you are the same people you saw yesterday and the day before and the month before. There is no variation, no surprise, no new input. Your brain, which evolved to seek novelty and respond to changing conditions, starts to shut down. Motivation drops. Tasks that used to feel important start to feel pointless. You go through the motions because the schedule says you have to, but the sense of purpose fades. You stop caring whether the experiment runs correctly or the maintenance gets done on time. You stop caring about much of anything. Depression follows boredom, not always, but often enough that researchers consider it a predictable outcome of prolonged isolation. The symptoms are classic: low energy, difficulty concentrating, loss of interest in activities, sleep disturbances, irritability, feelings of hopelessness. NASA has documented this in Antarctic research stations, in submarine crews, in long-duration space missions. One review noted plainly that a 12-month Antarctic stay can trigger an acute psychotic episode. 12 months. 1 year in an isolated environment with a small crew and access to regular resupply from the outside world was enough to push someone over the edge into psychosis. And that was on Earth. That was a place where, if things went truly wrong, you could evacuate. You could call for help, and someone would come, eventually. In deep space, there is no evacuation, there is no help. You are alone, and if someone breaks, the rest of the crew has to deal with it while continuing to operate a ship that cannot tolerate mistakes. Cognitive performance degrades too. Memory gets worse, concentration becomes harder, reaction times slow, decision-making deteriorates. One study found that up to 52% of people in isolated environments showed impaired memory and concentration, more than half. That is not an outlier, that is the norm, and the impairment is not subtle. People forget instructions, they miss details, they make errors they would not have made under normal conditions. In a normal environment, those errors might be annoying. On a spacecraft where every system is critical and redundancy is limited, those errors can be fatal. Then there is the sensory deprivation. Space is not just isolated, it is sensorially impoverished in ways that are hard to convey if you have not experienced it. On Earth, your senses are constantly bombarded with input. You see colors, textures, movement. You hear wind, birds, traffic, voices. You smell rain, food, cut grass. You feel temperature changes, humidity, the texture of different surfaces under your hands and feet. Your brain takes all of that input and uses it to construct a model of the world. The model updates constantly based on new information. That is how you stay oriented. That is how you know where you are and what is happening around you. In a spacecraft, most of that input disappears. The environment is monotonous. The walls are the same color every day. The lighting is artificial and constant. The air smells like recycled metal and plastic and whatever cleaning agents you use to keep the filters from clogging. The temperature is controlled. The sounds are mechanical. Fans, pumps, the hum of life support. There is no weather, no seasons, no day and night in the natural sense. The sun does not rise and set. It just sits in the same position relative to the ship unless you maneuver. And outside the window, if you bother to look, there is nothing. Blackness, maybe a few stars, but stars do not move, they do not change. They are just points of light in a void that stretches forever in every direction. Your brain does not handle that well. Sensory deprivation, prolonged and severe, distorts perception. Studies have linked it to hallucinations, anxiety, derealization, depersonalization, and transient psychotic-like experiences. People start seeing things that are not there, hearing voices, feeling presences. The line between what is real and what is imagined starts to blur because the brain, starved of input, begins generating its own. It fills the silence with sound. It fills the emptiness with shapes. And you, the person experiencing this, cannot always tell whether what you are perceiving is external or internal. That uncertainty is terrifying. It erodes your trust in your own senses. And once you stop trusting your senses, you stop trusting yourself. The absence of Earth is its own kind of trauma. On every space mission flown so far, Earth has been visible. A bright blue marble hanging in the black, close enough that you could see continents, cloud patterns, the Terminator line between day and night. Astronauts describe looking at Earth as a deeply emotional experience. It grounds them. It reminds them that they are not truly alone, that home is still there, still turning, still full of everyone and everything they have ever known. But on an interstellar mission, Earth disappears, not metaphorically, literally. A few months into the journey, Earth becomes just another star. A point of light no brighter or more significant than any other. You can point a telescope at it and confirm it is still there, but you cannot see it with your naked eye. You cannot see the oceans or the cities or the storms. You cannot see home. And that absence, that visual severance from the only world your species has ever known, has psychological consequences that no one has fully mapped because no one has experienced it yet. NASA has acknowledged this. One source noted that deep space missions add Earth out-of-sight conditions and communication delays of over 20 minutes one way, intensifying separation and nostalgia. 20 minutes. That is the light travel time between Earth and Mars at relatively close approach. For an interstellar mission, the delay is measured in years. You send a message home, 4 years later, maybe someone receives it. 4 years after that, maybe you get a reply. By the time you hear back, 8 years have passed. The conversation is not a conversation. It is an exchange of monologues between people who are aging at different rates, living in different contexts, experiencing different realities. And the further you travel, the longer the delay becomes, until eventually the delay is so long that communication stops being meaningful. You are not talking to Earth anymore. You are talking to the past, and the past does not answer. The social fabric disintegrates. On Earth, you are embedded in a network of relationships that extends far beyond your immediate household. You have family, friends, co-workers, acquaintances. You interact with strangers, you see new faces. You have the option, if a relationship goes bad, to walk away and find other people. In a spacecraft, that network collapses to the size of the crew, maybe 5 people, maybe 10, however many fit in the habitat you designed, and those people are all you have. There is no one else. If you do not get along with someone, you cannot avoid them, you cannot leave. You are stuck together for the duration of the mission, which might be decades, and the dynamics between you will determine whether the mission succeeds or whether it falls apart in a slow-motion cascade of interpersonal failures. The research on this is not encouraging. Interpersonal tension is listed as a major mission risk. Violations of privacy and territory can trigger irritability, withdrawal, performance declines, and cooperation problems. Classic isolation research describes a predictable pattern. Early in the mission, there is anxiety. Everyone is nervous, trying to adapt, feeling out the social dynamics. Then comes a period of relative calm. The routines are established, the crew settles in, but that calm does not last. After a few months, boredom and depression set in. People become irritable. Small annoyances, the kind you would normally ignore, start to feel unbearable. Someone chews too loudly. Someone does not clean up after themselves. Someone talks too much or not enough. These are trivial things, but in a confined space with no escape, trivial things become major sources of conflict. The violations of privacy are particularly difficult. You do not have your own space in the way you do on Earth. You have a sleep compartment, maybe a few cubic meters, and that is it. Everything else is shared. The galley, the bathroom, the exercise area, the workspaces. You are never truly alone. Someone is always nearby. You can hear them, you can smell them, you bump into them in the corridors. And over time, that constant proximity becomes suffocating. You start to crave solitude, real solitude, the kind where you can be completely by yourself for more than 5 minutes. But you cannot have it. The ship is too small, the crew is too close. And the longer the mission lasts, the more oppressive that closeness becomes. Territory becomes a battleground. On Earth, we mark territory unconsciously. This is my chair. This is my desk. This is my side of the bed. In a spacecraft, where space is limited and everything is shared, those boundaries are harder to define. But people still try. Someone claims a particular spot in the galley. Someone else always uses the same treadmill at the same time. And when those unspoken claims are violated, when someone sits in your spot or uses your equipment, it feels like a personal attack, even though rationally you know it is not. The emotional response is disproportionate to the actual offense, but that does not make it any less real. You get angry, you withdraw, you stop cooperating, and the mission suffers because the crew is no longer functioning as a team. The research describes end-of-mission effects that are particularly disturbing. As the mission nears its conclusion, some crews experience a surge of hostility or hypermanic agitation. The anticipation of finally getting out, of finally being free, ramps up the emotional intensity. People become more irritable, more impulsive, more prone to conflict. Or they become overly energized, almost manic, talking fast, sleeping less, taking risks they would not have taken earlier. Either way, the dynamic destabilizes at exactly the moment when the crew needs to be most cohesive, when the final tasks need to be completed and the landing or docking procedures need to be executed flawlessly. If the crew falls apart at that stage, the mission can fail in the last hours after years of success. Then there is the problem of psychiatric disorders. NASA has warned plainly that prolonged isolation and confinement can raise the risk for anxiety and depression, and that undetected behavioral issues may develop into mental disorders. Not might, Can, and not just mild mood disturbances, full psychiatric disorders, anxiety disorders, major depressive disorder, potentially psychosis. The agency screens astronauts carefully before missions, looking for any history of mental illness, any red flags that might indicate instability. But screening is not perfect. People can hide symptoms. People can develop disorders later in life that were not present during screening. And once you are on the ship, light years from Earth, there is no psychiatric hospital. There is no therapist. There is a medical officer who might have some training in mental health, and there are a few medications in the pharmacy if they were packed, and that is it. If someone develops severe depression, if someone becomes psychotic, the crew has to manage it with no outside help and no real resources. And meanwhile, the person who is suffering is still a member of the crew, still expected to perform tasks, still occupying space in a habitat that is already too small. The countermeasures we have are limited. NASA lists practical strategies that astronauts currently use: exercise, healthy eating, structured sleep and work schedules, leisure time. These help. They are not enough. Exercise helps with mood, but it does not fix isolation. Healthy eating supports brain function, but it does not replace human connection. Structured schedules provide routine, which is stabilizing, but routine also becomes monotonous, and monotony is part of the problem. Leisure time helps, assuming you have anything to do during that time. But how much variety can you pack into a spacecraft? You have books, movies, music, games. You have a limited library of media that you have already seen or heard multiple times. After a few years, you have exhausted everything. You have read every book. You have watched every movie. You have listened to every song until the lyrics are burned into your brain. And then what? You start over. You reread. You rewatch. Or you sit in your compartment and stare at the wall and try not to think about how much longer the mission has to go. Communication with Earth helps when it is possible. Astronauts on the ISS can send emails, make video calls, talk to family and friends in something close to real time. The delay is less than a second. It feels like a normal conversation. But on a deep space mission, the delay is minutes at first, then hours, then days, then years. You send a video message to your family. You tell them you are okay, you miss them, you hope they are doing well. Months later, you get a response. They tell you what has been happening in their lives. Someone got married, someone had a baby, someone died, and you were not there for any of it. You missed it all. And by the time you hear about it, it is ancient history for them, but breaking news for you. The emotional timeline is out of sync. You are grieving someone who died a year ago. They have already grieved, already moved on, and now they are trying to comfort you across a distance so large that the comfort arrives too late to matter. Or the communication stops entirely. People move on. They stop writing. They stop recording messages, not because they do not care, but because the distance makes the relationship feel abstract. You are not a person anymore. You are a memory. You are someone they used to know. And maintaining a relationship with a memory is hard. It requires effort, emotional energy, a willingness to keep reaching out even though the response takes months or years to arrive. Most people cannot sustain that. The messages become less frequent, then they stop, and you are left checking the communication logs, hoping for something new, finding nothing. The isolation is compounded by the fact that you cannot leave. On Earth, even in the most remote location, you have the option to leave if things get bad enough. You can quit, you can call for evacuation, you can walk away. In space, you cannot. You are locked in. The mission timeline is fixed. The ship is moving. There is no abort button that brings you home early. If you want out, the only option is to wait until the mission ends, and that might be decades away. You signed up for this, you agreed to the terms, but agreeing intellectually to a 40-year mission and actually living through year 5 when you are already exhausted and the thought of another 35 years makes you want to scream are two very different things. The crew dynamics can spiral. One person becomes withdrawn, another becomes irritable, a third starts making mistakes because their concentration is shot. The fourth tries to keep the peace, which exhausts them, and eventually they burn out too. And the fifth, who maybe was the most stable at the start, now has to carry the whole mission on their shoulders because everyone else is falling apart. That is not sustainable. Eventually, they crack too. And when the entire crew is psychologically compromised, the mission is in serious danger, even if all the hardware is functioning perfectly. There is no easy fix for any of this. You can design better habitats, give people more space, more privacy, but space is expensive. Every cubic meter of habitat volume is mass that has to be launched and accelerated. You can increase the crew size, thinking that a larger social group will be more resilient, but larger crews require more resources, more space, more complexity. And paradoxically, larger groups can sometimes have worse interpersonal dynamics because there are more relationships to manage, more opportunities for conflict. You can screen more carefully, selecting only the most psychologically resilient candidates. But resilience has limits. No one is immune to isolation. No one is immune to sensory deprivation. No one is immune to spending years in a tube with the same few people and no possibility of escape. You can provide better communication tools, virtual reality systems that simulate Earth environments, therapy protocols delivered remotely, medications to manage mood disorders. All of that helps at the margins. None of it solves the core problem. The core problem is that humans are not built for this. We are social animals. We evolved in tribes, in communities, surrounded by family and familiar faces. We need variety. We need novelty. We need the option to leave. Strip all of that away and we suffer. Not because we are weak, because the environment is fundamentally hostile to the psychological needs of our species. And the worst part is that the suffering is invisible to everyone except the crew. Earth will not know. By the time a message reaches home describing the psychological state of the crew, months or years will have passed. The information is outdated before it arrives. Mission Control cannot respond in real time. They cannot offer advice, adjust the plan, send help. They can only listen to recordings of people describing their deteriorating mental health and hope that by the time the message arrived, things got better on their own. Usually, they do not. This is not speculation. This is extrapolation from decades of research in isolated, confined, extreme environments. Antarctic stations, submarines, space stations. The patterns are consistent. Isolation breaks people. Confinement breaks people. Monotony breaks people. And the longer the exposure, the worse the damage. An interstellar mission is not a 6-month rotation on the ISS. It is not a year in Antarctica. It is decades, maybe a lifetime. And the psychological toll of that, the cumulative weight of years spent in a metal box with no escape and no end in sight, is something no human has ever experienced. We are guessing at what it would do, and the guesses are grim. So when you think about sending people to another star, when you imagine the ship and the trajectory and the destination, do not forget the minds. Do not assume that psychological resilience is infinite, that people can just tough it out if they are motivated enough. They cannot. The brain is an organ. It has limits. Push it past those limits and it breaks. Not in a sudden catastrophic way, usually, but in a slow, grinding collapse of function that leaves people alive but not okay, functional but not whole, surviving but not living. And if the crew arrives at the destination with their bodies intact but their minds shattered, what was the point? You did not send explorers, you sent victims, and the universe does not care. The universe does not notice. The ship keeps moving, the stars keep burning, and the people inside, the ones who sacrificed everything to make the journey, spend the rest of their lives carrying the scars of what the isolation did to them. But even if you could shield the crew from the psychological damage, even if you could design a habitat that kept them sane and healthy and functional, you would still have to build the thing. And building a ship capable of crossing light years, carrying people, keeping them alive, and arriving intact is an engineering challenge so vast that it makes everything we have built so far look like practice sketches. You solved the psychology problem, somehow. You screened the crew carefully, picked people with iron wills and stable temperaments, gave them therapy protocols and communication tools, and enough personal space that they did not strangle each other in year 7. You built a rotating habitat so their bones stayed dense and their muscles stayed strong. You shielded them from the worst of the radiation. You plotted a trajectory that avoided the densest molecular clouds. You kept them sane, or sane enough, for the duration of the journey. The bodies arrived intact. The minds arrived functional. You did everything right, except you still have not explained how you built the ship in the first place. How you designed a vessel capable of crossing 5.88 trillion miles, keeping people alive for decades or centuries, functioning without resupply, without maintenance crews from Earth, without the option to call home and ask someone to send a spare part. You have not explained how you engineered a machine complex enough to sustain human life, but reliable enough to run for longer than most civilizations have existed. That is not a minor detail. That is the entire problem, and it is a problem we have no idea how to solve. Let's start with the most fundamental question. How long does the trip take? That depends on how fast you go, and how fast you go depends on what kind of propulsion system you have. The fastest spacecraft humans have ever built, Voyager 1, is currently moving at about 38,000 miles per hour relative to the Sun. That sounds fast. It is not. At that speed, a trip to Proxima Centauri would take roughly 70,000 years. You are not sending astronauts. You are sending a tomb. So you need to go faster, a lot faster. And that means you need a propulsion system that does not exist. Chemical rockets, the kind we use to launch satellites and send probes to Mars, are out of the question. They are too slow and they require too much fuel. The amount of propellant you would need to accelerate a crewed spacecraft to even 1% the speed of light using chemical rockets is larger than the mass of the entire ship by orders of magnitude. The rocket equation, which governs how much fuel you need to reach a given velocity, is exponential. Add more fuel, and you need even more fuel to accelerate the fuel you just added. The math spirals out of control almost immediately. Chemical propulsion works for getting off a planet and moving around the solar system. It does not work for crossing interstellar distances. Ion drives are better. They are more efficient. They can run for years, slowly accelerating the spacecraft to higher and higher velocities, but they are also weak. The thrust is measured in fractions of a newton. A newton is roughly the force required to lift a small apple. Ion drives produce less thrust than that. They work by accelerating ions, electrically charged particles, to very high speeds and expelling them out the back of the spacecraft. The exhaust velocity is high, which means you get a lot of delta V, change in velocity, for a given amount of propellant. but the actual force pushing the ship forward is tiny. You can run an ion drive for a decade and still only reach a fraction of the speed required for practical interstellar travel. They are great for moving small robotic probes around the solar system. They are not enough for a crewed interstellar mission. So the conversation shifts to more exotic propulsion concepts. Nuclear pulse propulsion, for example. The idea dates back to the 1950s and a project called Orion. The concept is simple, in a way that borders on insane. You carry a payload of nuclear bombs, hundreds of them, maybe thousands. You drop them out the back of the ship, one at a time, and detonate them. Each explosion creates a shock wave that hits a massive steel plate mounted on the rear of the spacecraft, pushing it forward. The plate is mounted on shock absorbers to keep the acceleration from liquefying the crew. You repeat this process over and over, bomb after bomb, riding a series of nuclear explosions across the solar system and beyond. The math works. The thrust is enormous. The exhaust velocity is high. You could, in theory, accelerate a ship to a few percent the speed of light using this method. The problem is that you are setting off hundreds of nuclear bombs in space, and every bomb adds mass to the ship in the form of the bomb itself, and at some point you are hauling so much ordnance that the whole thing becomes impractical. Also, there is the minor issue that detonating nuclear weapons in space is currently banned by international treaty, and convincing the world to lift that ban so you can build a spaceship propelled by atomic bombs is not a conversation anyone wants to have. Fusion propulsion is the next step up. Fusion, the process that powers the sun, releases energy by combining light atomic nuclei into heavier ones. Hydrogen fuses into helium. Helium fuses into heavier elements. The mass of the products is slightly less than the mass of the reactants, and that missing mass gets converted into energy according to Einstein's equation E equals mc squared. A small amount of mass produces a huge amount of energy. If you could build a fusion reactor compact enough and efficient enough to fit on a spacecraft, you could use it to heat a propellant, expel it at extremely high velocities, and achieve the kind of thrust and efficiency needed for interstellar travel. The problem is that we do not have working fusion reactors, not practical ones, not ones that produce more energy than they consume. Fusion research has been ongoing for more than 70 years, and the joke in the field is that practical fusion power is always 30 years away. We can create fusion reactions in laboratories. We can even create them in experimental reactors like ITER, which is currently under construction in France. But those reactors are massive, expensive, and not designed for spaceflight. Building a fusion drive small enough and light enough to mount on a spacecraft and reliable enough to run for decades without maintenance is a problem that remains unsolved. Antimatter propulsion is even more speculative. Antimatter is matter with opposite charge. An antiproton has the same mass as a proton, but negative charge instead of positive. When antimatter and normal matter come into contact, they annihilate each other, converting their entire mass into energy. The energy yield is extraordinary. A single kilogram of antimatter reacting with a kilogram of normal matter releases as much energy as several tens of megatons of TNT. In principle, antimatter propulsion could accelerate a ship to a significant fraction of light speed using relatively small amounts of fuel. In practice, antimatter does not exist in large quantities anywhere in the universe that we can access. You have to make it, and making it requires enormous amounts of energy. Current production rates are measured in picograms per year. A picogram is a trillionth of a gram. You would need kilograms. The gap between what we can produce and what we would need is so vast that antimatter propulsion is not even on the horizon as a practical technology. It is a theoretical idea that works beautifully on paper and nowhere else. Some people bring up warp drives. The concept comes from general relativity, which allows, in principle, for the fabric of space-time itself to be warped in ways that could move a bubble of space faster than light without technically violating the speed of light limit inside the bubble. If you could create such a warp bubble and put a ship inside it, you could cross interstellar distances in subjectively short times without the time dilation effects of traveling at relativistic speeds. The problem is that creating a warp bubble requires exotic matter, a form of matter with negative energy density, and no one knows whether exotic matter exists or how you would produce it if it does. The math suggests that even if it is possible, the energy requirements are astronomical. One early estimate put the energy needed to warp a small region of space at more than the total mass energy of the observable universe. Later refinements brought that number down, but even the optimistic estimates require energy outputs far beyond anything we can generate. Warp drives are not engineering projects. They are thought experiments. They belong in the same category as time machines and perpetual motion devices. Fun to think about, not useful for solving the actual problem of getting humans to another star. So where does that leave us? With no propulsion system capable of moving a crewed spacecraft to another star within a human lifetime. Not with current technology. Not with anything we expect to develop in the near future. The best realistic option, if you are being generous with the word realistic, is a generation ship. A vessel large enough to support a self-sustaining population for the centuries or millennia it would take to reach another star at sublight speeds. Not a ship crewed by astronauts who signed up for a mission, a ship crewed by a community. People who are born on the ship, live their entire lives on the ship, and die on the ship, passing the mission down to their children and their children's children until someone, generations later, finally arrives at the destination. The concept is old. It shows up in science fiction as early as the 1920s. The idea is straightforward. Build a habitat large enough to house hundreds or thousands of people. Spin it to create artificial gravity. Fill it with everything a small society needs to function. Farms, water recycling systems, manufacturing facilities, schools, hospitals. Make it self-sustaining so that the population can survive indefinitely without resupply from Earth. Launch it toward a nearby star at whatever speed you can manage, probably a few percent the speed of light at best, and then wait. 1,000 years maybe, 10,000 years for the most distant targets. The ship becomes a world. The mission becomes a multi-generational project. The people on board become a culture unto themselves, isolated from Earth, preserving whatever knowledge and traditions they carried with them when the journey began. The implications are staggering. You are not just building a ship, you are founding a civilization. The people who board the ship at launch will never see the destination. Their children will not see it. Their grandchildren will not see it. Depending on the distance and the speed, dozens of generations might live and die in transit. The mission becomes the entire context of their existence. They are born into a world where the walls are metal, the sky is a ceiling, and Earth is a story their great-great-grandparents used to tell. Some of them might not believe Earth ever existed. It might become a myth, a religious story, a cultural memory so distant and abstract that it stops feeling real. You also have to deal with the fact that a population living in isolation for centuries will change. Genetically, culturally, linguistically, the people who arrive at the destination will not be the same as the people who left. They will speak differently. They will think differently. Their values, their beliefs, their social structures, all of it will have evolved in response to the unique pressures of living on a generation ship. They might not even consider themselves human in the same way we do. They are something new, a branch of the species that split off when the ship launched and developed in isolation for 1,000 years. And when they finally arrive at the destination, if they arrive, they will be strangers to Earth in every sense that matters. Then there is the question of whether a closed society like that can even survive for that long without collapsing. Human societies on Earth have access to resources, trade, migration, external input. A generation ship has none of that. It is a closed system. If the population grows too fast, you run out of space and resources. If it grows too slowly, you risk genetic bottlenecks and inbreeding. If a disease breaks out, you cannot import medicine or evacuate the sick. If a political conflict erupts, you cannot leave. You are stuck together, and the stability of the entire mission depends on the ability of that closed society to govern itself, resolve conflicts, maintain social cohesion, and pass down the knowledge and skills required to operate the ship. History is not encouraging. Civilizations collapse. Governments fail. Knowledge gets lost. And that is on Earth, where you have access to the rest of the world. On a generation ship, collapse is extinction. There is no backup. There is no rescue. If the society falls apart, everyone dies. Building the ship itself is an engineering nightmare. Start with life support. On Earth, you do not think about where your air comes from. The atmosphere is just there. Plants produce oxygen. You breathe it. You exhale carbon dioxide. Plants absorb it. The cycle runs itself. On a spacecraft, you have to engineer that cycle. You need systems that remove carbon dioxide from the air, split it into oxygen and carbon, and return the oxygen to the cabin. You need systems that recycle water, extracting it from urine, sweat, and condensation, purifying it, and making it drinkable again. You need systems that grow food, either hydroponically or in soil, using artificial lighting because there is no sunlight in deep space. And all of these systems have to run continuously, reliably, for decades or centuries without breaking. The European Space Agency has developed a prototype system called the Advanced Closed Loop System, or ACLS. It is designed for deep space missions. The system recycles carbon dioxide into oxygen using a combination of water electrolysis and catalytic reactions. Water gets split into hydrogen and oxygen. The oxygen goes back into the cabin. The hydrogen is combined with carbon dioxide to produce water and methane. The water gets recycled. The methane gets vented or stored. The system can recycle about half of the carbon dioxide on the International Space Station, saving roughly 400 liters of water per year that would otherwise need to be launched from Earth. That is impressive for a prototype. It is not enough for a generation ship. You need to recycle everything, not half, everything, because there is no resupply. Once you launch, whatever you have on board is all you will ever have unless you figure out how to manufacture it from raw materials. Current life support systems on the ISS recycle water and oxygen at about 70 to 80% efficiency. NASA's goal is to push the water recovery rate to 99%. That still leaves 1% loss, and 1% loss over a century adds up. You would need to carry reserves, buffers, extra capacity to account for the inevitable losses that occur even in the best designed systems. And you would need redundancy, backup systems, backups for the backups. Because if the primary life support system fails and you do not have a backup, everyone dies, not in a year, in hours or days depending on what failed. Then there is food production. You cannot carry enough food for 1,000 people for 1,000 years. The mass would be prohibitive. You have to grow it. That means you need farms, Hydroponic systems, probably, since soil is heavy and hydroponics can be more efficient in a controlled environment. You need grow lights, which require power. You need nutrient solutions, which need to be recycled and replenished. You need to grow a variety of crops to provide a balanced diet. You need to manage pests and diseases without access to earth-based agricultural supply chains. And you need to do all of this inside a closed environment where failure means starvation. Waste recycling is equally critical. Human waste, food waste, dead plant matter, everything has to be broken down and converted into something useful. Composting, bioreactors, chemical processing. The goal is to close the loop as tightly as possible. Ideally, nothing leaves the system. Everything gets recycled. Carbon, nitrogen, phosphorus, all the elements that make up organic matter get extracted from waste and fed back into the food production system. In practice, some loss is inevitable. Systems are not perfectly efficient. Atoms leak, materials degrade. You need a source of raw materials to make up for those losses, which means you either carry a massive stockpile of elements at launch, or you figure out how to mine asteroids or comets during the journey to replenish what you have lost. Either option adds complexity. Power is another massive challenge. You need electricity to run life support, lighting, computers, communication systems, propulsion, everything. Solar panels do not work in interstellar space. The sun is too far away. Its light is too dim. You need a different power source. Nuclear reactors are the obvious choice. Fission reactors, most likely, since fusion reactors do not exist yet. But nuclear fuel has a limited lifespan. Uranium-235, the most common fission fuel, has a half-life of about 700 million years, which sounds like plenty, but the reactor itself does not last that long. Reactor components degrade, fuel rods need to be replaced, control systems wear out. You would need to carry spare parts, replacement fuel, and the tools and expertise to perform maintenance and repairs over the entire duration of the mission. And you would need multiple reactors for redundancy, because if your only reactor fails, the mission ends. Everyone freezes, suffocates, or starves, depending on which system shuts down first. Material science becomes a limiting factor. The hull of the ship has to withstand micrometeoroids, cosmic radiation, thermal cycling, and mechanical stresses for centuries. Most materials degrade over time. Metal fatigues, seals crack, electronics fail. Radiation damages structural components at the molecular level, making them brittle. You need materials that are robust enough to last, or you need the ability to manufacture replacement parts during the journey. That means you need raw materials, fabrication equipment, and trained personnel who know how to use them. You are not just running a spaceship. You are running a mobile industrial base. Then there is the issue of self-repair. Things break, always. Pumps fail, pipes leak, computers crash, sensors go offline. On Earth, you call a technician. On the ISS, you can request a resupply mission or have the crew perform repairs using parts that were sent up in advance. On a generation ship, there is no resupply. There is no calling Earth for help. The crew has to fix everything themselves using whatever materials and tools they have on board. That requires a level of self-sufficiency we have never achieved in any spacecraft. The ship needs to carry spare parts for every critical system. It needs fabrication equipment capable of manufacturing replacement components from raw materials. It needs a population trained in engineering, maintenance, and repair. And it needs all of that to function reliably for centuries. Some have proposed automation, robots, artificial intelligence systems that handle maintenance and repairs without requiring human intervention. That helps, in theory. In practice, robots break too. Software has bugs. AI systems make errors, and if your automated repair system fails, you need humans who can fix it, which brings you back to the same problem. You need knowledge, you need skills, you need tools, and you need all of that to be preserved and passed down through generations of people who were born on the ship and have no direct experience with Earth-based technology. The social and cultural stability required to maintain that knowledge is itself a fragile thing. Imagine you are born on a generation ship. Your parents taught you how to operate the water recycling system. Their parents taught them. But what if somewhere along the line the knowledge gets lost? What if a generation decides that maintaining the old systems is not worth the effort, that they would rather focus on something else? What if a religion develops that forbids certain kinds of technology? What if a political faction seizes control and purges the engineers? These are not outlandish scenarios. They are things that have happened on Earth repeatedly throughout history. Knowledge gets lost, skills disappear, technologies are forgotten. The difference is that on Earth you can relearn, you can rediscover, you can import knowledge from other cultures. On a generation ship, if you lose the knowledge of how to fix the life support system, you die. There is no second chance. This is why closed-loop systems are so difficult. On paper, they make sense. Recycle everything, create a self-sustaining ecosystem, and you can survive indefinitely. In reality, closed-loop systems are incredibly sensitive to disruption. A single point of failure can cascade through the entire system. A contamination in the water supply poisons the crops. A failure in the air recycling system increases carbon dioxide levels, which reduces cognitive function, which leads to more errors, which causes more failures. The whole thing is a balancing act, and the longer the mission lasts, the more opportunities there are for something to go wrong. NASA and other agencies have studied this extensively. They know that current spacecraft life support is mostly open loop, meaning it relies on resupply from Earth. Moving to a truly closed-loop system is a major research goal, but it is not something we have achieved yet. The ISS recycles water and oxygen at high efficiency, but it still needs regular resupply missions. A generation ship would not have that option. It has to be closed-loop from day one, and it has to stay that way for the entire journey. Then there is propulsion, again. Even if you solve life support, even if you build a self-sustaining habitat that can last for centuries, you still have to move it. And moving a structure massive enough to house 1,000 people and all the infrastructure they need to survive is not easy. The ship would weigh thousands of tons, maybe tens of thousands. Getting that much mass up to a few percent the speed of light requires an enormous amount of energy. Chemical rockets will not do it. Ion drives are too weak. Nuclear pulse propulsion might work, but it requires carrying a huge stockpile of bombs and detonating them one after another for years. Fusion drives would be ideal, but we do not have them. Antimatter drives would be better, but we definitely do not have those. So you are stuck. You need a propulsion system that does not exist to move a ship that we do not know how to build on a mission that might take longer than recorded human history. And every component of that ship, every system, every subsystem has to function perfectly for the entire duration. One major failure, one critical system going offline with no way to repair it, and the mission ends, not in failure, in death. Everyone on board dies, and the ship becomes a tomb drifting through the void. That is the reality of engineering for eternity. It is not just hard. It is currently impossible. We do not have the technology. We do not have the materials. We do not have the knowledge. We can sketch out concepts. We can run simulations. We can build prototypes of individual systems, but putting it all together, building a vessel that can cross a light year and keep people alive for the journey, is beyond our capabilities by a margin so wide that it is hard to even see the other side. And even if we solved all the technical problems, even if we built the ship and launched it and everything worked, we would still be asking people to give up Earth, to leave the only world humanity has ever known, and commit themselves and their descendants to a journey with no return. The people who board that ship will never come back. Their children will never come back. The mission is one way. And the destination, assuming they reach it, is a star system we have barely studied, with planets we have never visited, where conditions might be completely unsuitable for human life. They are gambling everything on the hope that when they arrive, there will be something worth the cost. That is what it takes to cross 1 light year. Not courage, not ambition. A machine so complex and so reliable that it can function as a self-contained world for centuries. A population willing to live and die in transit. A propulsion system we have not invented. A closed-loop life support system we have not perfected. A social structure stable enough to survive longer than most nations have existed. And a willingness to accept that even if you do everything right, even if every system works and every generation fulfills their duty, the universe might still kill you. A single rock, a random collision, a cascade failure you did not predict, and it is over. So when someone says, we just need to build a better ship, what they are really saying is that they have not looked at the engineering. The ship is not just better. The ship is impossible with what we have now. And building the impossible, even if you had infinite money and infinite time, requires breakthroughs we cannot schedule. Fusion propulsion, closed-loop life support, self-repairing systems, materials that do not degrade, social structures that do not collapse. Every single one of those is an unsolved problem. String them together, make them all work simultaneously for centuries, and you are not talking about engineering anymore. You are talking about a miracle. And miracles, as it turns out, are not something the universe provides. The universe does not care whether you make it. It does not care whether your ship holds together, or your crew stays sane, or your life support keeps running. It has no opinion on whether humanity reaches the stars. It just sits there, vast and indifferent, waiting to see whether you can solve problems that might not have solutions. That is where we go next, to the final accounting. The cost, the impossibility, the reality that no matter how much you want to cross a light year, wanting is not enough. The universe sets the terms, and the terms are brutal. You built the ship, somehow. You solved the propulsion problem with technology that does not exist yet, but let us pretend you solved it anyway. You assembled a generation ship massive enough to house a self-sustaining population, engineered life support systems that can run for centuries without resupply, packed enough redundancy that a single failure would not kill everyone, and convinced 1,000 people to board a vessel that none of them would ever leave. You spun it up to create artificial gravity so their bones would not dissolve and their muscles would not atrophy. You shielded them as best you could from the radiation, knowing full well that the shielding would not be enough, but hoping it would at least slow the damage. You screened the crew for psychological resilience, gave them therapy protocols and communication tools, and enough personal space that they might not murder each other before the first decade was over. You plotted a trajectory that avoided the densest molecular clouds, accepted that some particle impacts were unavoidable, and launched. The ship accelerates. Slowly at first, then faster, climbing toward a velocity that might, if everything works perfectly, get the descendants of the original crew to another star system within a few centuries. You did everything right. You solved every problem. And now, sitting in mission control, watching the telemetry as the ship pulls away from Earth, you have to answer the question no one wanted to ask. Was it worth it? The universe does not care whether you think it was worth it. The universe does not have opinions. It does not evaluate your intentions, or admire your ambition, or reward your effort. It just enforces the rules. The speed of light is the speed limit. Radiation exists, and it damages biological tissue. Microgravity weakens bones. Isolation breaks minds. Particles moving at relativistic speeds hit like bombs. These are not suggestions. These are not obstacles you can negotiate your way around. They are features of reality, baked into the structure of the cosmos, at a level so fundamental that no amount of engineering or willpower will ever change them. You can mitigate, you can adapt. You can design clever solutions that reduce the harm, but you cannot eliminate it. And the longer the journey, the more the harm accumulates, until eventually the question stops being whether the crew will survive and starts being what condition they will be in when they arrive. Let us recap what you are asking them to endure. Start with time dilation. If you want the trip to be survivable within a human lifetime, you have to go fast, really fast, a significant fraction of the speed of light. Let us say 90%. At that velocity, time dilation becomes substantial. For every 10 years that pass on Earth, the crew experiences only about 4.5 years. That sounds like a gift. It is not. It is a severance. Every second the ship spends at relativistic speeds is another second that the crew falls out of sync with the rest of humanity. They send a message home. It takes years to arrive. The response takes years to come back. By the time they hear from Earth, the news is a decade old. Someone they loved has aged 20 years while they aged 9. The cultural references they grew up with are forgotten. The music they listened to is nostalgia for people who were not born yet when they left. And there is no pause button. There is no way to slow down, stop, and wait for everyone else to catch up. Time dilation is a one-way ratchet. Once you fall behind, you stay behind. The crew might experience the trip as a manageable chunk of their lifespan, but everyone they left behind experiences it as a generation. They do not come home to a hero's welcome. They come home, if they come home, as ghosts from a past that moved on without them. Then there is the radiation. Galactic cosmic rays, high-energy particles accelerated by supernovae and pulsars, passing through the ship constantly. Every day, the crew receives the equivalent of 10 to 20 chest X-rays. Every single day, for years, decades. The dose is cumulative. The damage is progressive. DNA strands break. Repair mechanisms fail. Mutations accumulate. Cancer risk climbs into double digits. Cardiovascular disease becomes more likely. Cognitive function declines as neurons are damaged and inflammatory markers rise in the brain, and there is no treatment that undoes it. No drug that reverses the cellular damage. You can manage the symptoms, you can try to slow the progression, but the damage is permanent. Every astronaut who boards that ship is accepting that they will spend the rest of their lives dealing with radiation-induced health problems, and that some of those problems will kill them. Not might, will. The only question is which organ fails first, and whether it happens before or after they reach the destination. Add to that the particle storm. At relativistic speeds, every hydrogen atom the ship encounters hits with the kinetic energy of a bomb. Dust grains hit like grenades. The interstellar medium, which looks empty from a distance, becomes a continuous barrage of high-speed projectiles that erode the hull, vaporize shielding, and produce secondary radiation every time they collide with the ship's structure. You can deflect some of it with magnetic fields. You can absorb some of it with sacrificial shields, but you cannot stop all of it. Some particles will get through, some will hit critical systems, some will hit people, and every hit is a roll of the dice. Most of the time, the damage is minor. A sensor goes offline, a section of hull needs repair, but eventually one of those impacts will hit something vital. A reactor, a life support module, a crew member standing in the wrong place at the wrong time. And when that happens, there is no calling for help. There is no rescue mission. The crew deals with it using whatever resources they have on board, or they die. The microgravity problem never goes away unless you spin the ship, and spinning the ship adds mass, complexity, and cost. If you do not spin it, the crew loses bone density at a rate of 1 to 2% per month. Muscles atrophy. The cardiovascular system deconditions. After a few years, their bodies cannot tolerate normal gravity anymore. If they ever return to a planet, they will not be able to walk. They will not be able to stand. Their skeletons will fracture under the load of their own body weight. You can slow the loss with exercise, 2 hours a day, every day, for the entire mission. But exercise does not stop the loss, it just reduces the rate. And over a journey lasting decades, the cumulative effect is catastrophic. The crew arrives, if they arrive, with bones like glass and hearts that cannot pump blood upward against gravity without causing them to faint. They are alive, technically, but they are not functional in any environment that has weight. Then there is the psychology: isolation, confinement, monotony. The crew is sealed in a metal tube with the same small group of people for years, decades, maybe a lifetime. They cannot leave. They cannot call for evacuation. If someone breaks, if someone develops severe depression or anxiety or psychosis, the rest of the crew has to manage it with no outside help and limited medical resources. The research is clear. Prolonged isolation increases the risk of psychiatric disorders. It impairs memory and concentration. It causes sensory distortions, hallucinations, depersonalization. The absence of Earth, the absence of new faces, the absence of anything resembling normal human social interaction wears people down. They become irritable. They withdraw. They stop cooperating. And when the social fabric of the crew disintegrates, the mission is in danger, even if all the hardware is functioning perfectly. You are not just asking people to endure physical hardship. You are asking them to stay sane in an environment specifically designed to drive them insane. And history suggests that most of them will not. So add it up. Time dilation that severs them from everyone they know. Radiation that poisons them slowly and irreversibly. Particle impacts that threaten the ship constantly. Microgravity that dissolves their bones and weakens their hearts. Isolation that erodes their minds. Every single one of these is a major hazard. Stack them together, run them concurrently for years or decades, and you are not talking about a difficult mission anymore. You are talking about a death sentence with extra steps. The crew might survive, some of them, if they are lucky, if nothing breaks, if no one snaps. But survival is not the same thing as success. Survival means arriving at the destination damaged, sick, psychologically scarred, and incapable of performing the tasks they were sent to perform. You did not send explorers, you sent victims. And the universe does not apologize. NASA knows this. They have framed it explicitly. Space radiation, isolation and confinement, distance from Earth, gravity fields, and hostile closed environments. They call it RIDGE. 5 categories of hazard that define human spaceflight in deep space. And every single one of them gets worse the further you go and the longer you stay. A trip to Mars lasts a few years. A trip to another star lasts lifetimes. Scale the hazards accordingly, and the conclusion is unavoidable. Interstellar travel, as currently conceived, is not survivable in any meaningful sense. You can engineer around the edges, you can optimize, you can reduce the risks marginally, but you cannot eliminate them. And the crew, no matter how well trained or how motivated, will pay the price. Their bodies will break, their minds will fracture, and the ship, no matter how well built, will degrade. Systems will fail. Components will wear out, and eventually something critical will break that cannot be repaired, and the mission will end. Not in triumph, in silence. The ship becomes a tomb, the crew becomes a statistic, and the universe, indifferent as always, keeps turning. So what is the point? Why would anyone attempt this? The usual answer is exploration. We go because we are curious, because we want to know what is out there, because the drive to explore is part of what makes us human. That is a beautiful sentiment. It is also insufficient. Curiosity does not justify sending people to die. Exploration does not require human bodies. We have robots. We have probes. Voyager 1 is currently more than 14 billion miles from Earth, still sending data, still functioning after more than 4 decades in space. It has no crew. It does not need food or air or psychological support. It does not suffer from radiation sickness or bone loss or depression. It just keeps going, doing its job, and when it finally stops, no one dies. We can build more. We can send them to other stars. They will not get there quickly. A trip to Proxima Centauri using current propulsion technology takes tens of thousands of years, but the probes do not care. They do not age, they do not get bored, they do not go insane, and when they arrive, whenever that is, they will send back data. Images, spectra, measurements, everything we wanted to know about the destination. No human suffering required. Some will argue that a probe is not the same as a human presence, that we need people there to make decisions, to adapt, to respond to unexpected discoveries in real time. That is true for some missions. It is not true for interstellar exploration. The communication delay is measured in years. A human crew at Proxima Centauri cannot consult with mission control when something goes wrong. They are on their own. A well-designed autonomous probe can handle that just as well as a human, and it can do so without requiring life support, food, water, or the massive infrastructure needed to keep people alive. The argument for sending humans, when you strip away the romanticism, comes down to symbolism. We want to plant a flag. We want to say we were there. We want to prove that humanity can cross the stars. But proving a point is not worth the cost, not when the cost is measured in lives, in suffering, in generations of people born into a metal prison they did not choose. There is another option, though it is not one most people want to hear. We could redefine what it means to be human in the context of space travel. Biological humans, as currently constructed, are not suited for interstellar journeys. We evolved on a planet with gravity, atmosphere, a magnetic field, and a stable environment. Strip all of that away, and we fall apart. But biology is not fixed. It can be modified. Gene editing, cybernetic enhancements, radical life extension. If you want humans to survive interstellar travel, you might have to change what a human is, strengthen their bones, make their cells more resistant to radiation, alter their psychology to tolerate isolation, extend their lifespan so that a century-long journey fits within a single lifetime. Some of that technology exists in early forms, Some of it is still theoretical. All of it raises ethical questions that no one has answered. If you modify someone so extensively that they can survive in deep space, are they still human? And if they are not, what exactly are you sending to the stars? A new species, a hybrid, a machine wearing human DNA? Or you skip biology entirely, upload minds into artificial substrates, digital consciousness running on hardware that does not need air or food or gravity. A ship crewed by uploaded humans could, in principle, survive indefinitely. The hardware can be repaired. The software can be backed up. There is no radiation sickness because there is no biology to poison. There is no bone loss because there are no bones. The psychological challenges remain, but they might be easier to manage if you can edit the software, adjust the parameters, reduce the negative feedback loops that lead to depression and anxiety. This is speculative. It is far beyond current technology, but it is not impossible. And if the goal is to get some version of humanity to another star, this might be the only way that works. The cost is that the thing that arrives is not human in any sense we currently recognize. It is a simulation, a copy, a ghost in a machine. And whether that counts as exploration or as something else entirely is a question without a clear answer. The philosophical implications are staggering. If you send a ship full of uploaded minds or genetically modified post-humans to another star, you are not extending humanity. You are creating a branch, a fork. The entities that arrive at the destination will have started as human, but by the time they get there, they will have diverged so far that calling them human is debatable. They will think differently. They will experience reality differently. They might develop their own cultures, their own values, their own sense of identity that has nothing to do with Earth. And if they do, what have you accomplished? You have not planted the flag of humanity on another world. You have seeded a new civilization that will grow in isolation and become something we cannot predict or control. That might be valuable. It might even be necessary. But it is not exploration in the traditional sense. It is speciation. It is the deliberate creation of a new branch of the evolutionary tree, one that splits off and never reconnects. And maybe that is the answer. Maybe interstellar travel is not something current humans can or should attempt. Maybe it is something we build toward over centuries. First, we colonize the solar system. We learn to live in space, to adapt our biology, to build self-sustaining habitats that do not require constant resupply from Earth. We develop the technologies we need: fusion propulsion, closed-loop life support, advanced AI, gene editing, mind uploading. We test them, we refine them. We make mistakes and learn from them in environments where failure does not mean the extinction of the crew. And then, maybe, a few centuries from now, when we have become something more resilient than we are today, we try. We send a ship, not a generation ship crewed by unmodified humans, but something new, something designed for the journey, something that can survive the radiation, the isolation, the time dilation, the particle storms, and arrive intact. It will not be us, not in the sense that we recognize, but it will carry something of us, our knowledge, our history, our desire to know what lies beyond the horizon. And maybe that is enough, or maybe we never go. Maybe we accept that 1 light year is too far, that the universe has set the terms and the terms are too steep, that some distances are not meant to be crossed by beings like us. We stay in the solar system. We build habitats around other planets, in the asteroid belt, in the Oort cloud. We send probes to the stars and learn what we can from the data they send back. We accept that there are limits to what we can do, not because we lack ambition, But because the universe does not bend to accommodate our dreams, there is no shame in that. The solar system is enormous. There is more space, more resources, more room to grow than we will ever need. We could spend 1,000,000 years exploring our own neighborhood and never run out of things to discover. But the stars will still be there, distant, unreachable, beautiful. And we will look at them the way our ancestors looked at the mountains before they learnt to climb, the way they looked at the oceans before they learnt to sail, with longing, with wonder, and with the quiet knowledge that some things, no matter how much you want them, remain beyond your grasp. Not forever, maybe, but for now, and for a very long time to come. The universe does not care. It does not care whether you make it. It does not care whether your ship holds together, or your crew survives, or your mission succeeds. It sets the rules, and the rules are brutal. 5.88 trillion miles is not just a distance. It is a barrier, a wall built from the fundamental constants of physics, reinforced by radiation and vacuum and time itself. You can throw technology at it, you can throw money at it, you can throw lives at it, and the wall will not move. It will just stand there, indifferent, waiting to see whether you can find a way over, under, or through. And if you cannot, if you fail, if everyone who tries ends up broken or dead or lost in the dark, the universe will not notice. It will not mourn. It will not remember. It will just keep expanding, keep spinning, keep burning, the way it always has and always will. That is the cost of crossing. Not just the engineering challenges or the physical dangers or the psychological toll. The cost is the recognition that the universe is not designed for you, that it does not want you to succeed, that it does not want anything, because wanting requires a mind, and the universe does not have one. It is a machine. A vast, uncaring, perfectly indifferent machine that runs according to laws you did not write and cannot change. And if you want to cross even 1 light year, you have to do it on the universe's terms. You have to accept the radiation, the isolation, the time dilation, the particle impacts, the bone loss, the cognitive decline, the psychological breakdown, all of it. You have to accept that the people who leave will not be the people who arrive, that the journey will change them, break them, or kill them. And you have to decide, knowing all of that, whether it is still worth trying. Maybe it is. Maybe the drive to reach beyond ourselves, to touch something new, to prove that we can cross the uncrossable, is worth the cost. Maybe the species benefits in the long run, even if the individuals who make the journey suffer. Maybe sending a ship to another star, even knowing that most of the crew will not survive intact, is justified by the knowledge we gain and the doors we open for future generations. That is a calculation you can make. It is not a calculation I envy, because at the end of it, you are still asking people to volunteer for a mission that will destroy them. And no amount of scientific advancement or philosophical justification makes that request less brutal. The universe does not care whether you cross 1 light year. It does not care whether you reach the stars or stay home or go extinct tomorrow. It is indifferent on a scale so vast that human concerns do not even register as rounding errors. You are a brief flicker of chemistry on a small rock orbiting an average star in an unremarkable galaxy. You have been here for a blink. You will be gone in another blink. And the universe will keep going, unchanged, untouched, exactly as it was before you existed, and exactly as it will be after you are gone. That is not a reason to give up, but it is a reason to be honest about what you are up against. The stars are beautiful, they are distant, and the distance is not just physical, it is existential. A gap so wide that crossing it requires you to stop being the thing you were and become something else, something harder, something stranger. something that can tolerate a journey no human was ever meant to survive. And if you decide to try anyway, if you build the ship and launch the mission and send people into the dark, knowing full well what it will cost them, then at least do it with your eyes open. Do not pretend it is an adventure. Do not sell it as heroism. Call it what it is: sacrifice. A deliberate choice to trade lives for knowledge. To send people into conditions that will break them so that maybe someday someone else can go a little farther. That is the cost. That is the price. And the universe, indifferent as always, will take your payment without saying thank you. 1 light year is 5.88 trillion miles. You cannot walk it, you cannot drive it, you can barely imagine it. And if you try to cross it, the universe will remind you, every step of the way, that you were never supposed to leave home in the first place. The radiation will remind you, the isolation will remind you, the time dilation will remind you, the particles will remind you. And when you finally arrive, if you arrive, you will step off the ship as something different from what you were when you left. Older, sicker, lonelier, changed in ways you cannot undo. And the question you will have to answer, standing on the surface of a world no human has ever touched, looking up at a sky full of stars you do not recognize, is whether it was worth it. Whether the cost, measured in years and health and sanity and lives, bought you something that justified the price. The universe will not answer that question for you. It does not care. It never did. So here is what 1 light year actually costs. Not in dollars or fuel or engineering hours, in something older. It costs the assumption that everywhere is reachable if you just try hard enough. It costs the belief that human ambition, given enough time and resources, can overcome anything. It costs the comfort of thinking that the universe, at some fundamental level, wants you to succeed. None of those things are true. The universe does not negotiate. It does not make exceptions. And it does not care whether the distance between stars feels fair to a species that spent most of its existence thinking the sky was a dome. You cannot cross a light year and come back the same. Not physically, not mentally, not temporally. The journey severs you from everything you were, everyone you knew, every context that made you recognizable as the person who left. And that severance is not a bug in the design. It is the design. The universe built distance into its architecture at a scale that punishes biology, that outlasts civilizations, that turns exploration into exile. You do not visit another star. You become estranged from your own. Maybe that is why we keep looking up anyway. Not because we think we can win, but because the refusal itself means something. Because a species that looks at 5.88 trillion miles and says not yet instead of never is a species that has not given up on the idea that the future might be larger than the past. The stars do not care. They do not notice. They will burn whether we reach them or not.